ASR system. Okay. Well, we will then explain how to build an ASR system for the Arabic language with TensorFlow, presented by Nourchene, Ferchichi, and Abir Korched from InstaDeep. For those who don't know InstaDeep, it's founded in 2014. InstaDeep is an EMEA leader in decision-making AI products for the enterprises, with a headquarters in London, an office in Paris, Tunis, Lagos, Dubai, and Cape Town. InstaDeep has built products such as its Innovel Deep Chain platform that tackle the most complex challenges across a range of industries. So InstaDeep has also developed collaborations with global leaders in the artificial intelligence ecosystem, such as Google, DeepMind, NVIDIA, and Intel. The company is part of Intel's AI Builders program and was named a preferred deep learning partner by NVIDIA. We also have GDG Carthage, who are present with us. GDG Carthage, or Google Developer Group Carthage, is an independent group active in North Africa and the MENA region. We usually organize events, meetings, and training related to Google technologies in Tunisia, like TensorFlow, machine learning, Android, Flutter, or even cloud and UX design for startups. And we are open to anyone interested in our activities. Our group allows you to connect virtually or in person with local and international developers to bring together great opportunities. So thank you for the three companies here with us. We will present a full TTS pipeline for transforming text-to-speech for a given language with Amel, Sellami, and Khalil, Rhouma from InstaDeep. And finally, we'll give an overview of the latest AI language models, trends, and improvements with Karim Beguir from InstaDeep. So every attendee here, if you have any question, you can refer to the Q&A section in Zoom. They will be answered after the talks. So we will start now with the first talk, Tunisian NLP challenges from building a language model to downstream tasks fine-tuning. The speakers will be Hatem Haddad. He is a co-founder and CTO at iCompass. He received a doctorate in computer science and information systems from University in Alps, France. His current research interests include natural NLP, machine learning, and deep learning. We have also with us Malek Naski. Malek, I'm sorry. Malek is a final year engineering student at the National Engineering School of Tunis, specialized in computer science. She joined iCompass in a year and works mainly on NLP systems. Her current interests involves mostly large-scale deep learning and NLP systems. So welcome to Hatem and Malek.
Thank you, Khalil, for the introduction. As Khalil introduced, we will talk about Tunisian NLP challenges from building a language model to downstream task fine-tuning. So I will start by having a general idea about NLP, mainly Arabic NLP, what was done before, and some revolutions that started since 2013 with this file, and that allow us today to have great products in the industry and in the market. So if we check the past in the next slide. So mainly for decades, we focused on MSA, the modern standard Arabic. So the NLP Arabic community focused only on this for decades. They worked on low-level processing, NLP processing, like stemming, lemmatization, part of speech, creating dictionaries, lexicons, but no one was talking about dialects. All the effort was done on the modern standard Arabic. And for me and for iCompass, this is not really our focus, because we believe that our people, they talk different languages. They talk different dialects. The MSA is the language that we use every day in formal way, so to write documents for administration, etc. But it's not our way of communication. So the Tunisian, for example, and I will talk a little bit at the end about the Tunisian characteristics. It's completely different from the modern standard Arabic. That's why for industry, we had very, very few Arabic NLP applications that was in the market until a few years ago. And this is because the Arabic language did not attract attention for big companies. So if we talk about big companies selling electro products or cars or etc., they didn't focus on the Arabic language. And when talking about these companies, they were telling me that anyway, you talk French or English in your country, and it's enough for you to have French products or English products. No need to go and work on your dialects. Another reason why we didn't have Arabic NLP applications in industry is that all the applications had very, very low performances. And this is for me because two reasons. The people working on NLP, at the beginning, they were linguistics. They were not really computational linguistics as we have today. And for a linguistic, it's just to find rules, grammar, etc., but not really programming a service or a software to solve problems. Another reason was also that all these products were time-consuming. And for industry to have a high time-consuming product, it's not enough to put it in the market. So what happened after? In the next slide, for me, what happened is a revolution that started in 2013. The day I saw this paper from Thomas Mikolov about the Word2Vec, for me, it was the beginning of a new era about how we can do Arabic NLP without going deep into all these details about stemming, lemmatization, part of speech. So now we can do a lot of things, and we focus on the performance rather than all the pre-processing steps that can take a lot of time and still very complex for the Arabic language. From here, we had Word2Vec, then we had Seg2Vec, Seg2Seg, etc. And we saw the performances of all the products going higher and higher. And in the next slide, I had Thomas as a keynote speaker when I organized the Cycling 2016 in Turkey as a keynote speaker. And talking with him, I told him, you made a revolution in the NLP field. And he told me, my friend, Word2Vec is just a candle in the dark. Soon we will have electricity. He's a very humble scientist, but a few years after, he was right. Because in the next slide, we had the electricity, and this electricity is the BERT model. When the BERT model was released by Google in 2018, 2019, it made a big difference in the state of the art in different NLP applications. So the idea here is to create a big natural language model. And from this language model, we can do any fine-tuning with it to apply it in different applications. Karim at the end will focus more on this and will show why we need this language models and why it's important today to have these language models. But still here we are at the electricity era. For me, what will come after, and this is, we'll see it in the next slide, it's your future. The future is yours, and I believe that with TwinBird and with your creativity, we will have the nuclear power. And this nuclear power will make a big difference in the everyday Arabic country people. We will have new products in the markets that are more focused on Arabic, on dialects. We are talking about Industry 4.0 that will come soon in our countries. we are talking about smart cities, smart cars, and all these products, they need to interact with people in their own dialect. That's why today we released the TuneBird. It's for you, for young generation. For me, I will stop at the electricity level, but I will leave you the nuclear level for you to use all the creativity that you have. And I believe you have a lot of energy, a lot of motivation, a lot of creativity to create new products that will make our future and your future. So if you allow me to give you some tips or recommendation, I see many CVs that students focus on Coursera courses, Udacity, etc., etc. This is good, a good beginning, a good step. Maybe because today at the universities we don't have curriculum or courses up to date to talk about NLP, to talk about artificial intelligence. It's a good starting point with this Coursera or Udacity courses, but still not enough to be expert in the NLP field. My recommendation is to go for more advanced courses. I recommend the Chris Manning course from Stanford. He made all his courses are online. They are very, very good. They go from low complexity to high complexity with labs, with practice, etc. He was my mentor for many years, and he is one of the biggest name today in the NLP. And last but not least, what I recommend is to practice, practice, practice. This is how we can progress, because practice is the main master. Better to practice than to spend hours on videos on YouTube, etc. With practice, you can learn more and faster. So they saying this, if you don't have any questions, I will allow, I will invite Malek to talk to us more in detail about how we created TuneBird and what is a language model. Khalil, if there is no questions until now, we can move to the next section.
Yeah, of course.
So thanks, Hatem. Hi, everyone. This is Malek from iCompass. I participated in building TuneBird, aka the first Tunisian pre-trained language model, which is a collaboration between InstaDeep and iCompass. And as Hatem said, BERT actually revolutionized the NLP field in these last couple of years. And we actually started seeing people all over the world building language-specific BERT-based models. And even though a multilingual BERT does exist, which was trained on many different languages, many dialects and languages are still underrepresented today, just like the Tunisian dialect. So we said to ourselves, why not a Tunisian BERT? And in order to dive deeper into reasons why we needed to build a Tunisian BERT, we will actually have to understand how BERT works and why does it even exist. So as Hatem said, BERT is actually a way to build, you can build actually language models that are basically a representation of a natural language of your choice. And you can afterwards fine tune it on a specific downstream task. So here, the tricky part is that the most data hungry and the most computationally demanding part is actually the pre-training part, or the part where we actually build the language model. And the bright side here is that this part is an unsupervised training and it does not require any labeled data. And you know how expensive annotating data and labeling it can be. So this is a huge advantage for us. So we can actually build this language model, and then each person that has a labeled data set that is much smaller can actually perform downstream tests and still achieve state-of-the-art results on them. So, and since the Tunisian dialect data is scarce, especially the annotated data, Timbered here can be the solution for many of us, especially students and people who do not have access to large labeled data sets. So we actually provide the major building block of this model, which is the language model. And then you guys can perform downstream tasks with your own labeled data sets. So why TensorFlow? And this is a TensorFlow Meetup. So we will talk about our TensorFlow implementation of the Timbered model. And as you may know, the first BERT ever was released by Google and made with TensorFlow 1. And during this collaboration, we actually wanted to accelerate the process. We wanted to perform the training in a distributed fashion. And since the original code base was actually written in TensorFlow 1, it's kind of outdated. We actually had to seek code that is written in TensorFlow 2 in order to take advantage of TensorFlow 2's mirrored strategy that makes us able to perform distributed training. So luckily, TensorFlow has a GitHub repository that is called Model Garden, and it has implementations of many popular state-of-the-art models, including BERT and other huge models. And it helped us to migrate the original code to native TensorFlow 2 and take advantage of the mirror strategy, and now we can actually distribute. So as for how we actually built the model, and guys, I cannot stress this enough, you can do this yourselves, and all of the script, all of the code, you'll actually have to make minor changes, but the major building blocks are already there for you. So if you wish to build any language model in any dialect or language that you wish, you can actually do this. So how did the process, how was the process for us? So we had to collect and scrape data, typical. We had to clean it, process it, and finally fire up the training. So for the data collecting part, we actually went and sought data from many online sources, many social media, Facebook, Twitter, Instagram, YouTube, you name it. And we actually wanted to make sure that the data is well representative of what Tunisian people are saying online. So we had to cover as many topics as possible, as many regional dialects as possible. And we included, for example, music, politics, TV shows, news, casual conversations between random people, etc. So the Tunisian text that we chose that the Tunisian text that we train on is written in Arabic letters only. And we wanted our data set to be as large as possible because too much is never enough with these kind of models, and especially BERT-based models. And we ended up with having actually 500K lines of Tunisian text written in Arabic letters. So as for the data cleaning, we had to do the typical things, remove emojis, punctuation, symbols, non-UTF characters, etc. And we had to also do a processing to keep only sentences that are in Arabic, in Tunisian Arabic, because we also had sentences in French, English, Arabizi, which is Romanized Arabic letters with also numbers, etc. So we had to do this type of pre-processing. And the thing that is important here is that we do not do any lemmatization or any typical NLP pre-processing, simply because the model actually has to receive the sentence as it is naturally said and written by a normal human being, so that it actually can understand the context, because BERT is the first deeply bidirectional and contextualized model. So it has to get the entire sentence in order to understand how the language or the dialect works in a natural way. So now we can actually move on to creating the data in a format that BERT actually needs. And first of all, we have to build a vocabulary. And here we use the word piece tokenizer, which is going to take the entire data set. It is going to prepend the subwords which occur in the middle of words with number sign. And the subwords occurring at the beginning of words are going to be unchanged. And if the subword occurs both in the beginning and the middle of words, both versions are going to be added to the vocabulary. So like this, we build a vocabulary that has subwords of our data set that is supposed to be representative of the Tunisian dialects, right? So afterwards, we add special tokens or special control symbols that are required to train BERT, such as the padding token, the unknown token, the beginning of sentence, the end of sentence token, the masking token, etc. Because BERT works through masking words and trying to guess them, so that it builds knowledge on the certain dialect or language that we're working on. And we also add some unused or placeholder tokens in order to use them in the future. So for example, if you want to take the language model and train it even further, and if there are tokens that do not exist in the vocabulary, they're going to be added in these placeholder tokens. So here, for example, we have our tokenizer, we have our vocabulary file, and we try to tokenize this sentence that is written in Arabic. So here you can see that the letters here are Latin, and it does not understand them because our vocabulary actually contains, as we mentioned before, the Tunisian that is written in Arabic characters. So here we can see that the tokens are unknown, unknown, unknown. So in this sentence, for example, which is written in Arabic, we can see that the tokenizer does the tokenization and adds the number sign to the subwords. And here too, so the sentence is from YouTube, I guess. So this sentence has been tokenized, as you can see, according to our initial data set and therefore our vocabulary file. So as for generating pre-training data, and just to remark here, guys, maybe you can find frameworks that can actually do all of this for you. But in the original BERT, this is how it happens. So this is what happens under the hood. So for the data formatting part, we generate pre-training data that is compatible with the BERT format. So what happens? First, we have the tokenization. The data set is broken down into tokens. So each sentence is broken into tokens. And we add the needed tokens at the beginning, at the end of sentences, and we pad the sentences that are, which length is less than the maximum sequence length that we set. We actually have to pad them, and we convert each token into their corresponding ID in the model. And you have the scripts to do all of this in BERT's repository, so don't worry about that. And as for the architecture, we actually had to keep the BERT-based architecture unchanged. And it is basically a stack of bidirectional transformer encoders. We keep the standard architecture, we did not change it. And the total parameters here are going to be 110 million. As for the hyperparameters, we were actually inspired by previous works because the pre-training takes days and it's really expensive and really time consuming to just tune the hyperparameters for the pre-training part. So we were inspired by previous work, and we chose the hyperparameters to be this way. So as for the training, and now we fire up training, we did it on 4 NVIDIA Tesla Volta 100 GPUs using TensorFlow's mirrored strategy to distribute the training. So this was done on one node on Google Cloud Platform. And you may ask yourselves, what is the mirrored strategy and how does it work? So here actually we use something that we call in the state-of-the-art data parallel synchronous SGD, or synchronous stochastic gradient descent. So how this happens is that the parallelization here is happening on the data, not on the model. So all of the variables and model graph are going to be replicated on the GPUs, and the data is going to be evenly distributed on the GPUs. So for each step, if we have a batch of data for the entire model, this batch is going to be split into sub-batches, and each sub-batch is going to be processed by a GPU, and this GPU will calculate the gradient. So it will do the forward, the backward pass, and it will then, they will send their gradients and they will be synchronized all over the GPUs. and they will be reduced, or the mean is going to be calculated. And afterwards, the weights are going to be updated all over the GPUs once again, and each GPU is going to be making the calculation on each new batch of data. And each time, this is going to happen going forward and backward with the weights. And this is how the weights are going to be updated and synchronized at the same time between different GPUs. So this is quite interesting, especially if you have large models, and especially if you want to reduce the training time. So here we actually reduce the training time by processing bigger batches at a time, holistically speaking. So if we see it from a higher level, we can see that the batch size is quite big, but it's actually just smaller batches to each GPU. So yeah, this is actually a representation of how it actually happens. The weights are going to be calculated and sent back to calculate the mean. The entire weights of the entire network are going to be updated again and sent back to GPUs, etc. So you can find TuneBERT on GitHub, on InstaDeep and iCompass's repositories. And you will also find an implementation in PyTorch using the Nemo toolkit. So you can use whatever you want. You can use the TensorFlow implementation, the PyTorch implementation. You're actually free. So yeah, if you have any questions about this part, I'll be glad to hear them and answer them. And yeah, thanks for listening.
Thank you, Malek. So yeah, we have a lot of questions. Okay, can we fine-tune TuneBERT to create a Moroccan version?
I'm sorry?
Can you fine-tune TuneBERT to create a Moroccan version?
I believe that TuneBERT was created for the Tunisian dialect. Even though there is similarities between the Tunisian dialect and the Moroccan one, but creating a language model for the Moroccan is more relevant in this case than fine-tuning TuneBERT for the Moroccan language. Going from a dialect to another dialect, words, they have a different sense or meaning. That means a word in Tunisian that can have a specific meaning when the same word in Moroccan can have a different meaning. That's why I suggest to create a new language model for the Moroccan language.
Okay, thank you. So Khadija said, thank you for your presentation. We recommended practicing, but how exactly could you please give us some specific tips on where to start?
I can talk of my case. When I started working on NLP, I check a problem solved in English or French, and I tried to do the same for Arabic and create my own solution for the Arabic language. That means take any kind of problem, named entities recognition or information retrieval, and apply the same that was done for English to your dialect. This is how I used to practice. No need to be a computer engineer or specialist in NLP or have a degree in NLP to do this. Anyone can today learn by itself.
Thank you. Okay, next question. How did you decide the amount of data needed for the pre-training?
This is, as I said, we actually wanted our data set to be as large as possible. And this is actually the amount that we could scrape at the time. And maybe you guys can contribute with even more data, because you actually have the option to train the model even further on further text and that you guys have. And maybe you can even enhance the model. So yeah, that's all we could do at the time. So.
We have to know that the Tunisian dialect has some specificities. One of them is the switching language. So when we talk Tunisian or we write, We switch from Latin to Arabic characters. We use some French words or English word in the same sentence. So this amount of data, it wasn't the original amount of data. We collected much more, but then when it comes to the cleaning and filtering, a lot of data was a mix between Arabic and Latin. In TuneBird, we used only the Arabic alphabet, so words written in Arabic alphabet. Just after, I will talk about the Latin Tunisian. And I saw a question about this, and I will be happy to talk a little bit about this problem a little bit later.
Yeah, sure. You can do it, Hatem, if you want.
So if there is no more questions, we can move to the next section.
We have another question. Is
Yes.
TuneBird available and accessible to us as students to use it in our projects? Is it open source?
Yeah,
It's open source, it's free to use. You have the links, and we will put the links also at the end of this presentation. Everything is public and free for the students, for also people working on research. This was made for them. Between InstaDeep and iCompass, we decided to put it free since the beginning to allow our students and allow our researchers to carry on their practice and also their research PhD or master.
Thank you. So a lot of Tunisian dialect data on the internet is available in Latin letters. How do you deal with this kind of data?
Okay, I will talk, if you allow me, I will talk about this in the last part of the speech. I will focus in this main problem.
Okay. So Sarah said there is a previous attempt to make an English to Tunisian dictionary known as derjaninja.com. I don't know if you know this. Do you think the data used for this dictionary can be used to build or update a model? She said also Derja Ninja has more than 17,000 entries.
17,000 is not enough. Previous works, as I mentioned, they focus it on building dictionaries, lexicons, all this knowledge base about the words that we use, the relation between these words, or linguistic, like synonymy, etc., etc. But I believe, and this is what was proved by linguistics, that dialects are a very, very, how to say, the words in a dialect, they change meaning. A dialect is a very dynamic language that is every day a new language. You know this Tunisian dialect, but also all the other dialects from Algeria or Morocco. Every day we have a new word. Every day we have a new expression. Every day the same word can change meaning in few days. And that's why building a static dictionary or static lexicon, for me, it's not very accurate. I would prefer a language model that we can update once in a while with new entries, then building manually a dictionary, and after we cannot update.
Okay, thank you. Next question by Iskander. How do you handle the fact that several styles of speech in Tunisian Arabic are not represented online? The way old people talk, or the way a lot of people talk in special contexts, like in certain public marketplaces, as special religious or social events. Basically, when you use online sources, a certain demographic of Tunisian speakers are vastly overrepresented, while others are poorly represented or unrepresented altogether.
Okay. That's why when we collect data, we try to make it as large as possible and include the maximum of topics, the maximum of people expressing themselves in social media or in internet. And after, this is the fashion, or this is the good part of artificial intelligence, that we can handle and we can process a lot of data in the same time.
Mm-hmm.
After, if someone would like to focus in demography or speaking ways in different regions, it's possible with TuneBot.
Okay,
and
you.
Also, if I can add something, actually, in our training data set, we also included data that is about Tunisian stories that are written in the Abdelaziz Arawi style. So there is actually some data that is representative to that is not real present online, but is present in our data set. Certainly, it is underrepresented but we're actually working towards enlarging the data set, and you guys can help too, since this is an open source project.
Thank you. So Sarah asked if would it be easier to use an Arabic programming language to avoid the clash between Latin letters and Arabic entries. I don't know if there is some Arabic programming languages.
I didn't get the question. No?
Yeah, me too. I think she's asking if we use an Arabic programming language. I don't know if there is an Arabic programming language. Okay, Sarah, if you can re-ask the question. So, the question of Skander was already answered. So I thought you have used PyTorch with NVIDIA NeMo also. I don't know. Is that true or not?
Yes.
Okay.
Yeah, you can find the both models on the repositories.
On GitHub. Okay. So Amir asks if does the pre-training enabled the data for TuneBot contain MSA in addition to Tunisian dialect? Also, is it possible to use BERT embeddings to measure the similarity between the dialectal word and its corresponding MSA?
It's a very philosophical question. What's the difference between Tunisian dialect and MSA? There is an intersection between them, of course. Some words have the same origin, or we use some MSA in our Tunisian dialect. Maybe in the next, we can show how to identify, how to use TuneBot to fine-tune a downstream task to identify between two different dialects. We can use it also to identify Tunisian dialect and MSA. So if you allow us to move to the next section, we can have some practice and show this. Malek, please, if you move to the next one.
Yes.
Which is a demo about how to use TuneBot in one specific downstream task.
Okay.
So in this example, we'll actually see how to fine-tune TuneBot on a downstream task, which is dialect identification. And this task will actually identify Tunisian and Algerian dialects, which is a challenging task because these dialects are actually similar in some ways. So this demo was made by Abir, my colleague. So thank you, Abir. Let's watch together.
We are going to show you how to fine-tune TuneBot on the dialect identification task using Google Colab. First, we clone Google Bird directory. We install then the appropriate libraries. We import the TAD dataset. Dataset is divided into train, dev, and test. Let's have a look at the data distribution. The data contains comments in Tunisian dialect annotated as 0 and in Algerian dialect annotated as 1. Here we show you the number of comments in each set. The data is balanced. We have the same number of comments in each dialect. We move now to the fine-tuning step. we need the checkpoints, the vocab and the configuration files of TuneBERT language model. As we mentioned earlier, they are available in iCompass or InstaDeep GitHubs. We run the runClassifier.py file with a batch size of 16, a max sequence length of 128, and for 4 epochs. During the fine-tuning, checkpoints will be stored in the output directory. Once the fine-tuning is complete, we move to the prediction step. So, we set to predict as true. TestResults.tsv contains the prediction probabilities of each class. Finally, we want to measure the performance of our model. We get an accuracy and a weighted average F1 score of 91%. That's amazing!
That's amazing indeed. So if you have any questions about this specific task or about the fine-tuning, just ask away.
Khalil, do we have any questions related to this section?
Yeah. So they're asking, how does TuneBERT compare to other models for regional dialect in the MENA region?
But actually, this is the first one dedicated to a specific dialect. What we have in the state of the art are different language models, but they are a mix of a lot of dialects. So we can find Gulf, Egypt, Levantine in the same language model. What we did with BERT is that we focused only on the Tunisian dialect. And that's why the pre-processing and filtering step was very important to us to keep only Tunisian text. So you have a lot of different language models in the state of the art going for MARBERT. I will talk about this a little bit later, RBERT, etc. But they are really a mix. And what is interesting is that the amount of data in these language models, when it comes to Tunisian, Algerian, or Moroccan, are very, very few. And I think they are not really appropriate to use them for local dialects in North Africa.
Okay, how would you evaluate TuneBERT on fine-tuned text summarization task, knowing that BERT architecture outperform BERT in this task? I don't know if you got it.
We didn't do this actually, but the one who asked the question can practice on this.
Okay. How much is the training time for TuneBERT and what hardware or cloud you have used?
So for the Nemo or PyTorch model, it took 5 days. We had to stop the training for the TuneBERT with the TensorFlow implementation at 2.5 days, according to the loss method. So as for the hardware, as I mentioned before, we trained on one Google Cloud Platform node that has 4 GPUs, 4 Tesla Volta 100 GPUs.
Okay, thank you. So someone noticed while he fine-tuned TuneBERT that the first sentence is skipped when doing predictions. Is that a normal behavior or did he do something wrong?
Sorry, first sentence is?
He noticed when he fine-tuned TuneBERT that the first sentence is skipped when doing the prediction. I don't know.
What do you mean the first sentence is?
The first sentence is skipped. I don't know. Anonymous, can you explain more?
If you have any issue, you can actually raise an issue on GitHub. There is no problem.
Okay. So are you planning to implement further functions for TuneBERT, such as offensive language detection?
Why not? Well, anyone can do it now. Since TuneBERT is available and is public, anyone can use it for any fine tuning task that he can imagine. That's why I said I let your creativity to the next step. We created TuneBERT for you, but now it's up to you to use it and to play with it.
Okay. So TuneBERT doc will be improved on the future because for now I don't find it that user friendly. I don't know. What is TuneBERT doc?
Documentation, I guess, the README file on GitHub.
I don't know. He said that it's not user friendly. Okay.
You can create an issue on GitHub, and we will be happy to answer your question or modify our doc to make it more easier for everyone.
Okay. So that's it, I think.
Okay.
Okay. Thank you. So in the last part of our talk, I will focus a little bit about the Tunisian. As you know, everyone is talking about the Arabic as the Latin version of the Arabic language. That's what people use in the Middle East or North Africa to write on social media or SMS or etc. But at iCompass, we find that there is a big difference between Arabic, which is at the origin was an Egyptian version of the Latin, which is called Arabic English, Arabic Anglisi. That's why it's called Arabici. And at iCompass, when we did our study, we find out that our Tunisi, we call it Tunisian in iCompass, is completely different from the Arabici used in the Middle East. When we use 3, 5, 7, 9, it's different from what Middle East countries use in social media. So recently in 2020, we had a paper in ICLR, and we defined the Tunisi as the Romanized alphabet used to transcribe informal Arabic or informal Tunisi for communication by the Tunisian social media community. And we have a lot of examples to show that they are completely different from what Middle East people use. So in the next step, I jump on the first question. Can you show us the next slide, Malek, please? Yeah, indeed, what Tunisian use on internet, it's mainly Latin character. And we had some studies here about Tunisian Facebook comments, and almost 81% is Latin character. And if we talk more general, in Tunisian social media, we are also at a high level of Latin character. And a small part also 30%, but I guess now it's more. This was 2019. I guess statistics in 2020 will show more code switching. That means in the same sentence, they can use different kind of characters, Arabic and Latin in the same language. That's why in iCompass, we paid attention at this specific way of writing of Tunisians on the social media. And that's why we created the Tunisi. So in the next slide, we proposed in 2020 a dataset, annotated dataset for sentiment analysis Tunisian Arabic dataset. So that's Latin way of writing. At the beginning, we created the small dataset, about 10K commands annotated manually as positive and negative. And still this one is balanced and public, but still a small data set to be used in real applications or to make a real progress in this fight. So that's why in the next slide, we created the second version of this. It's the Tunisia version 2. It's 100K data set. It's the largest data set dedicated for the Tunisian Arabic. It's almost balanced. so we can use it for different experiments. We included also some neutral commands here to make it as multi-label data set. And we used this for different experiments using the Marbert that I talked before in the next slide, giving quite good performances to do this exercise with Latin character Tunisian text. So here we are almost at 80% of accuracy and F1 micro for both classification or multilingual, multi-label classification or binary classification. And this data set, in the next slide, we use it to create a competition with Zindi at beginning of this year. It was a very, very popular competition. It's about social media sentiment analysis for Tunisian Arabic. There were 740 data scientists from all over the world, different countries. We were really surprised to see students from Ivory Coast, from Chile, from Indonesia, working on the Tunisian sentiment analysis data set. At the beginning, we were happy that the top three were Tunisian, and the second one is a mix between a Japanese team and Tunisian team. We were happy, yes, because for a long time, there was a student from Israel who was top one ranked. And we were really surprised to not see our Tunisian students achieving high performance in this. We made this last year, and we are thinking now about creating more competitions for the students, opening our data sets or part of our data sets publicly to be used by the Tunisian or the Arabic community as a competition. It's another way of practicing, which is very, very interesting. And I ask all the students or researchers to participate in these competitions. This dataset is also available online. It's free. So in the next slide, we have all the references. We have the TwinBERT references that you can use. We have also the Tunisi dataset, which is publicly available. And finally, feel free to ask us any and contact us with any question. There is no stupid questions on this file. Any question can be interesting. If you have any idea about competition, about creating a new data set, feel free to contact us, and we are open to any collaboration. Thank you.
Thank you, Hatem. So, question: what are the use cases of this?
Of the Tunisia?
Yeah.
Same as in Arabic NLP, any kind of use case that you can think, from named entity to sentiment analysis, hate speech detection, fake news. There is a lot. It's very, very large. Yeah. We explored only a very small part, but still a lot to explore.
Okay. The Tunisian dialect is quite limited in terms of vocabulary items, and this results in words having multiple meanings, sometimes something and its opposite. So how does TwinBERT deal with the polysemy in the Tunisian dialect?
I really don't agree with that Tunisian has a very small vocabulary. From memory, the dataset that we used for BERT, it's about 400K different words. Right, Malek?
500K lines of text, actually, and much more words.
Do you have the number of words, different words, unique words?
I think they're about 8 million or something like that.
Yeah, it's huge for two reasons. The Tunisian vocabulary is very, very rich, and every day we have new words coming. The way of writing, since it's on social media, and for the Tunisian dialect, there is no rules about grammar or the way we write things that make it very, very sparse, and we have a different words. Polysemy, we can handle it with any machine learning or a deep learning program to find out what are the connections between words, and we can do classification about synonymy, polysemy, etc., etc. But it's still a very rich vocabulary, and it's very interesting to work on it. And the same for Moroccan and Algerian, I guess it's the same same observation.
Yeah. Can something like MT5 or maybe multimodal multitask embeddings like MUM be used to handle Tunisi and Tunisian written in Arabic alphabet simultaneously?
I didn't get the question. Sorry, Malek, if you have an idea, please feel free to answer.
I think we can actually try with the MT5 type of language models, and I think that every innovative thing in the NLP world on any language can actually be tried on the Tunisian dialect, and we can actually see what it gives. So as you can see, we're actually experimenting and seeing what we get.
Oh, perfect. So last question. Is there a way to fine-tune by importing the model directly in TensorFlow/PyTorch? I would like to fine-tune TuneBERT by adding some layer and freezing some node via the CMD commands way. It's like technical question here.
Yeah, I believe so, because it's actually a checkpoint. So it's a checkpoint file that you'll actually take and do whatever you want with it. You can actually train it further. You can add layers to it. You can fine tune it on a task. The basic, I mean, the most important thing here that we release is actually the checkpoint. So you can do whatever you want with it.
Yeah, perfect. The same way as we did dialect identification, you can just import a checkpoint and then use it for any application as you imagine.
Okay, thank you to Hatem and Malek for this very interesting talk and very informative Q&A. Thank you very much to iCompass. We go to our next talk with Nourchene, Ferchichi, and Abir Korched for building ASR systems for the Arabic language with TensorFlow. For those who don't know Nourchene, she is an AI research engineer at InstaDeep, Tunisia. She has deep skills in natural language processing. She has worked on challenging research projects focusing on the latest advanced NLP models. She has also delivered product projects responding to real-world business cases. For Abir Korched is an AI research engineer at InstaDeep also. She holds a strong background in natural language understanding and speech recognition tasks. She has developed deep learning models to solve real-world problems related to understanding and recognition of human languages, with emphasis on low resource languages. So welcome to Abir and Nourchene.
Hello, everyone. So I'll start by sharing my screen. Are you able to see the screen now?
Yes, we can see the screen. Hello, everyone.
Okay, so thank you everyone for attending this meeting. I'm very happy today to be part of this TensorFlow Meetup in Tunis. And in this presentation, we will introduce or help you learn how to build your automatic speech recognition model for ASR or for Arabic language using TensorFlow. So I'm Nourchene Ferchichi, research engineer, and I have with me Abir. Hello, Abir.
Hello, everyone. I am Abir Korched, AI research engineer at InstaDeep, mainly working on NLP tasks. I'm so happy to have you with us, and I hope that you will enjoy this session.
Okay, so this is the outline of this presentation. We'll start by a general introduction to in which we will talk what is ASR in general. We'll go through some of the application and the challenges. We'll introduce a basic, standard, but very efficient pipeline, and then some of the data set, especially the Arabic and the North African dialects that we can use. We'll introduce how you can build a deep neural network, acoustic model, and how you can build on top of it a language model in order to make your model more efficient. And we'll end up with a Jupyter Notebook demo using TensorFlow. We'll have a summary in the conclusion, and we will leave the last 15 minutes for a Q&A session. What is ASR? ASR is just the abbreviation of 3 different words: automatic, speech, and recognition. And it is the intersection between 2 different fields. The first field is the computer science, which is the science of understanding computers and computational systems. And the second field is the linguistics, which is the science of understanding the human language. So the global or general output of a ASR system should be that we would have a speech, and then we would transform it into a text. So for example, here, we would have as an input وقع إعلان الجمهورية التونسية في 25 من شهر جولاي في عام 1957. And we would expect our model to predict this written text. وقع إعلان الجمهورية التونسية في 25 من شهر جولاي في عام 1957. So the question here is ASR still part of the research, or we can use it actually in our daily uses? And the answer to this question is definitely yes. There are a lot of industries that are using the ASR. First of all, the telecom industries. We are creating some kind of conversational chatbots that are there to enhance the customer support by responding to your questions, resolving your technical issues, and even providing you personalized advice for a preferred service in the telecom industry. And then the second one is the marketing. So for the marketing, we are creating voice search engines such that you can record a description of a product you are looking for, and then you will have a great accurate product search responding to your use case. And today we hear a lot about Internet of Things. We hear words like smart TVs, smartphones, smart cars, and smart houses. And the common thing between all of those words is that you give them a kind of instruction in a vocal way, and then you get back. This is very interesting, as you can do a lot of things in a parallel way without even using your hands. And a last field is the healthcare. So nowadays we use digital assistant to help you in medical guidance. You can call your digital assistant and tell him how you feel. You can feel a little bit of fatigue. You can have a high temperature, and the digital assistant will ask you to, for example, get a little bit of rest, drink a lot of vitamin C's, and maybe take a test of coronavirus. And also the digital assistants are used internally with the medical staff by having access to information, especially administrative information, in a quick and an easy way. Here after is a very interesting application that actually uses the Arabic language, which is called مساعد Google. So مساعد Google manages your tasks, plan your days, and get your answers. All you have to do is to say, okay, Google, and the model or the مساعد Google will answer you in Arabic, telling you, for example, مرحبا كيف يمكنني مساعدتك. I will, for example, ask him about the weather, ما هي حالة الطقس اليوم, and I will get at an answer. الطقس المشمس، درجة الحرارة 32 درجة مئوية. So I'll leave now the floor for my colleague Abir.
Thanks, Nourchene. Now we are going to talk about the challenges. So the area of ASR is being discussed from past few decades, and it's still an open research area. And it's still not easy to reach flexible solutions that satisfies the user. And this is mainly due to some challenges to overcome. Let's talk about a few of them. We will talk about, first of all, about the challenges from a linguistic perspective. Actually, there are many sorts of variations, like the speaker. If you have, for example, a model which is tuned for one speaker, the model will find it really hard to generalize on other speakers. As we might already know, each speaker has its own characteristics. The environment may also influence the quality of the data. Having a noisy environment or speaking in a closed environment may cause some echo or reverberation, which deteriorate the quality of the audio and makes it hard for the ASR model to recognize very well the text. So it's really important to find ways to pre-process your data and clean it correctly. Other challenges are related to the accent. If you want to have an ASR model that could recognize a language, you need to make sure that for each language we have different speakers and each speaker has its own accent. So we need a robust model that could handle and understand the different accents. Disfluency and stuttering also could cause some problems for the model and makes it so hard to recognize words. Code switching is also a challenge for the ASR systems. As you can see here at the bottom right, an example which shows a text which contains Arabic letters, and we have a July, which is an English word. So for an ASR system who is mainly trained in a certain language, for example, for the Arabic language, you will find that he will not recognize the Latin characters, but he will, as you can see here, he tries to predict it the way he understands it. For this particular challenge, we need to find some ways to pre-process our transcripts if they contain some Latin characters. We need to transform Latin characters into Arabic characters, and we write them the way we hear them. And there are also other techniques that we could use, which are end-to-end models, which perform language detection. They could detect language, and based on the language which was detected, we can perform the recognition. And there are other paralinguistics problem related basically to the emotional state of the speaker. Maybe as an example, the intensity of the signal may differ from basing on the emotional state of the speaker, whether it is he is happy or angry, and so on. So let's now move to the second part, where we will talk about the characteristics of the Arabic language. Actually, there is a difference between the spoken and the written language caused mainly by the absence of diacritics. Let's see the example, which is on the bottom left, where you can see this verse. If I would ask someone to read it, I'm pretty sure that the majority of us will end up reading it not in a correct way because of the absence of the diacritics. Okay, when we add the diacritics, we can read them correctly. Without diacritics, we see them all the same word, alam, alam, alam. But when we add the diacritics, we can hear the difference between the different words. Alamun, alamma, alam. You can see here there is a difference when we add the diacritics. And when coming to ASR systems, this is really important, and the system really needs this information to improve its performance. But unfortunately, in real public data sets for the Arabic, the majority of the data sets are not diacritized. You might need to find tools that will help you to diacritize your data in order to improve the performance of your model. So let's move now to talk about the challenges from a machine learning perspective. As we already know, when we talk about deep learning especially, we have two main problems, which are data and compute power. So especially when we talk about the ASR for Arabic and low resource languages, there are now lots of resources which are available and that we could use to get good performance. I think that's it regarding the challenges. Let's now introduce some keywords related to the ASR. So I will pass over the speech to my colleague Nourchene to carry on this part.
Thank you, Abir. So in the next slides, we will go through what a standard easy ASR pipeline would look like. And here we go. So when I start speaking, all starts with those two words that I will be saying. For example, I take the same example, Al-Jumhuriyya Tunisiya. And when I'm saying those two words, I'm generating some kind of vibration in the air, which is translated into an acoustic energy. This acoustic energy can be captured by any acoustic device, such as a microphone. And this microphone has the ability to transform this acoustic energy into an electrical energy. The electrical energy can be measured easily and then plotted into a function of the amplitude in function of the time. And this is exactly what we call an audio signal or a wave file or a waveform. So here, if we have a look at the plot, we can easily distinguish between two blobs, which actually correspond to the two spoken words, Al-Jumhuriyya and Al-Tunisiyya. So the higher my voice will be, or the higher pitch I will be using, the more energy I will be generating, and then the higher values of amplitudes will be printed in the plot. And next step would be to extract all or most of the information from those audio signals. So we use here what we call a spectrogram, and it is a way of transforming a function of amplitude in terms of time to a function of frequency in terms of time. And we use here an algorithm called FFT, or fast Fourier transformation. There is a lot of math behind this. We will not get into details in this presentation, but I highly recommend you to go and read more about it. But the main idea behind this is a simple feature or a simple part from the wave file is actually composed of many frequencies. Some of the frequencies are even not human heard. And the sum of those frequencies are what we call frequency component. When all summed together, we get what we call a spectrogram. So the spectrogram is actually the input of my deep neural network acoustic model, and it has as goal to map the relationship between the audio signals to the phonemes. Here, the phonemes are the characters that I'm pronouncing. It could be ha, ha, or even a composition of two, khat, fa, fat, etc. And then we will put the language model. Why are we adding a language model? Because the acoustic model has only meaning about phonetics and or acoustics, and has no meaning or background of language. So this is why we add a language model, to give the probability distribution over sequences of words given the context of the speech. Finally, we have as an output the transcripts, which are the written text. We have the hypothesis or predictions, and the ground truth or the real text that we should compare with. And at this stage, we would like to compare or to see how our model is performing. So we would like to use a good metric. And the most known metric that is used for ASR is the WER, or the word error rate. And it calculates the number of errors averaged. And we have three types of errors. The first one is the substitution, when the model predicts a word while it gets some errors in some characters in the word. And the second error is the insertion, when I don't say a word, but the model predicts it. And the last one, the deletion, which is the inverse, when I say a word and the model does not predict. And then we average by the total number of words in the ground truth. I'll leave the stage for my colleague Abir now.
Thanks, Nourchene. Now we're going to introduce some data sets which are commonly known in for the ASR with the Arabic language. Let's talk about a few of them. We have mainly, next slide, please. Thank you. So we have three well-known data sets for the Arabic language. The first one is the Arabic speech corpus, which is an MSA data set for the standard Arabic, and consisting of 3.7 hours. The second one is Common Voice Arabic, which is also an MSA data set consisting of 77 hours. The third one is the Arabic speech recognition resources, which contains more than three, but for the ASR we have three data sets, MGB2, MGB3, and MGB5. The first one is for the MSA and some dialects, and the second and third one are for dialects. For the MGB2, we have 1,200 hours. For MGB3, we have 15 hours of Egyptian recordings. And for the Moroccan dataset, we have nearly 14 hours. And for these last three datasets, they are mainly scraped from YouTube, and they had been transcribed manually. So as you can see, there is not a lot of resources which are public for the Arabic. So this is why we suggested we tried to suggest some techniques in order to collect your own data set or to augment it. So for this suggestion, we would like to suggest scraping audio files from or recordings from YouTube or other resources, and then you need to segment audio files, because in general we work with audio files in the range of 0 to 16 seconds, just to avoid getting some memory issues. And then we will need to transcribe them. And for the transcription, we can, if there is a trained ASR model, even with a low performance, you can use it to transcribe the segmented audio files, and then you can double check the transcription, or you will end up manually transcribing them. This is a good way to create your own data set. Another way to enlarge your data set is by applying data augmentation techniques. Here we're going to cover a few of them. Basically, these techniques could help the model be more robust to many forms of variations, such as adding noise to your dataset, speed perturbation, help the model there are other techniques, that help the model to be more speaker independent, such as modifying the speech. And by modifying the speech, if you have, for example, a data set for male voice, and you would like to have a data set that contains voices for kids and female-like voices. So playing with the pitch could help you to have that kind of data set and vary your data set. In the demo later on, we will see some examples of these techniques. So yeah, let's move to the next slide. So then in the next part, we're going to introduce a deep neural network architecture for solving ASR problem. So I will let the floor for my colleague Nourchene to talk about this.
Thank you, Abir. So in the next slides, we'll go to introduce one of the deep neural network architecture for an acoustic model. So as you can see, that was already created, and then we add some of convolutional layers. We can choose the number of layers the way we want, and then on top of that we add recurrent neural networks, and of course the number of layers is up to you. Finally, we add a fully connected layer, on top of which we add a connectionist temporal classification, or a CDC. So let's go into more details on how this actually works. So as I said, you have the spectrogram, and then we should split it into simple, which are parts of the, let's say, the image. Those are split into time O, time 1 until time n. Those are the input of the CNN model. Why did we choose a CNN? Because convolutional neural networks have proven efficiency into extracting meaningful information or features from the images, and the spectrogram can easily be seen as an image. This is why CNN is a good option here. Then we add the RNN. RNN are known to be efficient for sequence modeling. And here, when I am going to say a character or a word, it mostly likely be dependent on the previous characters that I said or the previous word that I mentioned. So this is why we use RNNs. And there are multiple kinds of RNNs we can use. It could be GRUs, LSTMs, or even bidirectional GRUs or bidirectional LSTMs. And at the last step, we add the CTC, which is a kind of classification layer that will predict or output all the possibility prediction for each character. And the characters here are part of our vocabulary, which are the Arabic characters alef, b, t, etc., adding to them the space. So when I don't say anything, the model should be predicting the space. And here, for example, for our same example, Al-Jamhuriyya Tunisia, the first more likely character to be predicted should be the alef, then lam, etc., until predicting the whole word or then the whole sentence. I leave this stage for Abir.
So in this part, we're going to talk about a technique that could enhance the performance of the acoustic model. So let's move to the next slide, please. So the output of the acoustic model, as we can see, is the CTC matrix, as we explained earlier, which contains the probability of the likelihood of each character at each time step. As you can see this example here, we took an example where in our vocabulary we have mainly two characters, A and B, and this is the blank token. And we have in this matrix the probability at each time step. T0 is the first time step, and then we have T1. At each time step, we have the probability of each character. And this is, as we said, this is the output of the acoustic model. Now the question is, how could we use this matrix in order to get our transcriptions? Here we can talk about two techniques, two algorithms, which are the greedy search and beam search decoding. Let's explain them more in detail. For the greedy search, for the first part, the greedy search mainly concatenates most probable characters per time step. For T0, for example, we will look into the character which has the highest probability. In this example, the character with the highest probability is the blank character, which is nothing. So we will take it. Then we move to T1. At T1, also the most probable character is blank. So the output of this matrix, or the prediction or the transcription, would be nothing using the greedy search algorithm. Now moving to the beam search algorithm, which is a well-used strategy for dealing with sequence-to-sequence kind of problems. And this algorithm mainly creates iteratively text candidates. As we explained for the greedy search, we take the best path. At each time step, we take only the most probable characters. But when it comes to beam search, we're going to extract the top K candidates. We will not end up having only one sequence with the highest probabilities. We will have K candidates. And the K is the beam width. We specify the beam width, how many candidates you would like to have at the end. And it works as follows. We will explain it through this tree. So initially, we don't have anything. Always, we are using the same matrix here, which contains the probabilities. Initially, we don't have anything. At the first stage, at T0, we have three possible characters, A, B, and nothing. We will put them all. And we will just keep the two best candidates, which are A and nothing. We will move to the T1, the next stage, and we will do the same thing and keep the two best candidates. So in T1, we have in this the first node, we have A. Then we have we can add after A, B, or A or nothing. And for the other node as well, we have nothing, and after nothing, we could have A, B, and nothing. And we calculate here at this stage the conditional probability, and then we could decide to take the most probable sequences. Yeah, and we iterate like this over all the time steps in order to get finally the K candidates. So this is the main difference between greedy search, which gives us only one candidate with the best path, and the beam search gives us K candidates. So what's the problem with these algorithms for both greedy search and beam search decoding? We use the output of the acoustic model, which may not understand the context and tends sometimes to make some spelling and linguistic errors. And also, it will find it as an acoustic model. It will find it hard to distinguish between homophones. Even for a human, if we, I would say, asa, which may mean disobey or a piece of wood, they are written differently. And if I don't give you the context, you will not end up, you will not understand what do I mean. I mean a verb, or I mean, I meant a name. So given the context, will probably will improve the results of the model. So this is why we try to add a language model on top of the acoustic model in order to give some context and try to improve the performance of the acoustic model. So mainly the language model is trained on a massive text corpora, and the standard approach for the ASR is using n-gram language models. And there are some techniques who relies on transformers. In this presentation, we're going to talk only about the n-gram models. For the n-gram models, mainly you can train them using KNLM, which is an open source library. And yes, let's now take, let's see how we can fuse the beam search decoding with the language model. As we said before, the beam search will output k candidates, and for each candidate we have a score from the, which is the probability of the sequence from the acoustic model. Apart from this, we will add another score which is related to the language model. So the language model will attribute a score for the each candidate, and the final score would be a combination between the acoustic score, language model score, and the sequence length. And we have some tunable parameters, which are alpha and beta. You can tune them to get better results, best performance. I mean, in terms of word error rate. Let's now move to a comparison between to have an idea about the beam search decoding, beam search plus language model decoding, and the greedy search. We have always the same example, which is وقع إعلان الجمهورية. So for this example, this is the first table, sorry, is the output of the beam search decoding plus language model. This is the final score. The first column is the final score, and then we have the three candidates. The best one is the first, the highlighted one. And we have highlighted some difference between the ground truth and the predictions. As you can see here in the ground truth, the number 25 was written in digits, but for the language model, would find it hard to predict numbers. He only learned to transcribe words the way he hear it, or yeah. So this is why the output here, you can find it written in characters, al-khamisi wal-ashrin. Another thing is July. For July, he will not write it in Latin characters, because the model we have was trained on Arabic letters, so would not recognize other characters which are not in its vocabulary. So for the comparison in the next table between the greedy search and beam search language model decoding, there is a major difference here between the greedy search and beam search language model decoding in the word July. For the word July, for the greedy search, he has write it or transcribed it the way we pronounce it. So he write it July. But when we use the language model in fusion with the acoustic model, you can see here that July was transformed, or it gives a favor to Yulu, because Yulu is part of its vocabulary, of the vocabulary of the language model. So he will prioritize words that are in its vocabulary. So mainly the language model are can be used to correct some misspelling characters and improve very well the performance of the acoustic model. But when it comes to out of vocabulary words, it's really so the language model will not tend to give good results for out of vocabulary words. So yeah, this is it. Now we have covered the theoretical part. It's time to move to the practical part. So I pass over the speech to Nourchene to talk about, to introduce the demo.
Thank you, Abir. So can you see the Jupyter notebook now? Okay, so here we go. So in this Jupyter notebook, we will be using TensorFlow to create an ASR system based on DNNs. So there will be 3 major steps. The first step is to pre-process our data, which is some kind of or a massive input of acoustic mode, or voice recorded. And then the second step would be to create the architecture of the model, the same that we introduced in the presentation, a CNN plus an NNN plus a CTC decoder. And in the final step, we will train actually the model, then run some inference on some unseen data. And here we go. So let's start with the first step here in the pre-processing or the transformation of the data set. We'll be using mainly 2 packages, the Librosa and the PyAudio, which are built-in modules for some basic audio functionalities. We start by importing the Librosa and we give the path of the audio file, which is the same file we used in the presentation. We specify the sample rate, and sample rate is actually the number of points or values that we are going to take into consideration from the wave file. It's a way of transforming a wave file into NumPy arrays, and we load the data. So the type is actually numpy.nd array. Then here we would like to see the audio duration. We use also Librosa, so it's about 9 seconds. The total number of samples is calculated by the sample rate multiplied by the duration of the audio file. And overall, we have more than 155 samples or points, or which coincides with the number or the dimension of the tensor representing the audio file. Here we can hear the audio.
إعلان الجمهورية التونسية في 25 من شهر جولاي في عام 1957.
Okay, so to hear the voice here, we use the IPython display that displays the audio file in Jupyter notebooks. We would like also to see the amplitude in function of time. We use 2 libraries, the Librosa, also the matplotlib for plots, and we can display here the wave plot, and we see the amplitudes varying from negative to positive values in terms of time. And here we have 9 seconds, which is the overall size or duration of the audio file. Then we would like to transform the audio file into a spectrogram, and the Librosa actually has the implementation of the algorithm of the TFF we introduced in the presentation. So we just have to call the method Librosa.stft to transform the wave into a plot of hertz. Here represents the frequency in terms of time, and the frequencies varies also from negative to positive values. And the negative, as actually here the blue ones, are mainly those that humans cannot hear. So the main information are hidden here somewhere that we should be able then to extract to have the final transcripts. We introduced also in the presentation some kind of data augmentation in case the data is not sufficient enough. Here we use 2 major Python packages that we should pip install, the wave augment and the NL pod. So we just have to pip install them and then call them in a cell, and we transform our audio file into a torch audio. And finally, we can start with the first type of augmentation, which is adding noise. So first, we should generate the noise, which is a mathematical function. And then we add this generated audio or this generated noise to our voice, which is the X, and we can hear it using the ipd.audio.
وقع إعلان الجمهورية التونسية في 25.
So you can hear here a background noise that was generated and added to the audio file. Then the second type of augmentation is the speed perturbation. First one is the speed down. We should use a factor between 0 and 1 added to our audio file, and here after you can hear the result.
وقع إعلان الجمهورية التونسية في 25.
And in case we would like to have a speed up, we should choose exactly the same function, just changing the factor to a number between or a tuple between 1 and 2, and we apply it and we can hear the results.
وقع إعلان الجمهورية التونسية في 25.
Okay, there is also two other types, or one type that could be modified is the modification of the pitch. It could be a pitch up. When we use a factor, a positive factor, and we apply it, we get this result.
وقع إعلان الجمهورية التونسية في 25 من شهر جولاي.
So this is a more kind of a kid voice if our data is not representing kid voice enough. And in the pitch down, we use the same, we can choose the same number, but in a negative way, and we get this output.
وقع إعلان الجمهورية التونسية في 25 من شهر جولاي.
So this is more like an old man or an old woman or a male voice. So I'll keep now I'll let Abir continue on the same Jupyter notebook.
Thanks, Nourchene. So in this part, we're going to go through a TensorFlow implementation of an ISR model to recognize the Arabic speech. We will just go through the basic steps in order to help you understand the different steps to create an ISR model. So as the first step, we need to prepare our data set. We need to specify just the path of our data set with the CSV file using pandas. As you can see here in our data set, we have two columns, the path of the audio files and then the transcriptions. You can see here that the transcriptions are written in backwalter. You can have the transcriptions in Arabic script or backwalter. Backwalter is just a character map from Arabic to Latin characters. You can see here an example. We use LangTrans in order to convert backwalter into Arabic script. Here is an example. For our case, we're going to use the transcriptions in backwalter. For the modeling part, we're going to use a deep ASR implementation of Deep Speech 2. Deep ASR, is an open source implementation of different automatic speech recognition architectures. It supports mainly two architectures. They use Deep Speech 2 and Deep ASR network. The model architecture we are going to use in our case is Deep Speech architecture. We have just explained throughout the presentation, so we're not going to dig deeper into explaining the different the architecture. Let's talk about the input of the model. As you can see, the input is the spectrogram. So it's something like this, which is the MEL spectrogram. So we have 161, which is mainly used when conventionally used when using a sample rate of 16 kilohertz. In our case, we are using sample rate of 16 kilohertz, and the x-axis is the time. So for each record, we could have different times. Each one has its own duration. So for the Deep ASR package that we are going to work with, doesn't support Arabic. So we made some changes in order to make it work with Arabic language. First of all, we need to configure our pipeline. We need to specify what kind of features we're going to use as input for our model. In our case, we're going to use spectrogram, and then we need to specify the vocabulary. You just need to specify the language. In our case, we added the Arabic language to the scripts in order to recognize the Arabic, to get the Arabic characters. In our case, the alphabet would be the backwalter characters. Then we need to specify the dimension of the input output to our model. You need just to call the get model get deep speech, or if you would like to use the other model, which is deep ASR network, you just call the model, which is implemented in the package, specify the input output to your model, and then we need as another step to to choose the optimizer. In our case, we choose to work with the default optimizer, which is Hatem optimizer. You need to set your hyperparameters. Then you for this package also there is we have the choice to use either a greedy search decoder or beam search decoder with the language model. So we choose to work with the greedy search. And then, all right, you need to set the pipeline, you put it all together, and then you start the training, as simple as that. Just call the pipeline, fit, and give it the training data set and batch size and the number of epochs. This is the summary of the model, the same architecture we explained before. For the sake of this demo, we didn't use a large data set, and we just took a sample from MGB2 dataset, which is an MSA dataset, in order to make the pipeline work on an Arabic language and to show you the whole pipeline from building the model and to testing the model on real use cases. Here we can move to the second part, which is the model testing or the inference, where we can make some predictions. So here is an example. So the highlighted one is the reference, and the prediction of the model is in this cell, the highlighted one right now. So as you can see, as we said, before, we used a sample of the data to make the demo work for the Arabic language. And for the deep speech architecture, they mentioned in their paper that they need a large enough data set in order to get good enough results. They have trained for English, for example, on around 11K hours in order to get good results. So for our case, if you would like to work with this architecture, so make sure you need to have a large enough data set, or there are other techniques that you can use, either transfer learning. You can take, for example, a model which was trained on another language and fine-tune it on your task if you don't have enough data. So mainly this is it. Let's move to the conclusion. So I pass over the speech to Nourchene.
Thank you, Abir, for this demo. It was very useful. I hope it was useful for everyone here also. So in this presentation, we presented what ASR is. We went through some of its main challenges and data sets that you can use for Arabic and low resource languages that are North African dialects. We built a DNN model on top of which we can add a language model to improve its performance. But this is just an introduction for this ASR field. For those who are really want to learn more about this field, I really recommend you to learn more and about the new techniques such as transfer learning and fine-tuning, and maybe read some of the latest research papers talking about models based on transformers such as the Wave2Vec, also more complicated architecture based on convolutional neural networks architectures such as QuartzNet or CitriNet. So this was the full presentation. I hope that we have still time, yes, 15 minutes for a Q&A session.
Yeah, thank you, Nourchene, thank you, Abir. So we have some questions. Can you, how can you Tunisian ASR model understand that Potlik and Gotlik are the same word, pronounced by speakers of different regions?
Mainly, you need to have a data set which contains this difference. The acoustic model will try to to transcribe the speech the way he hear it. So if you have a data set which contains different accents, it will help very much the ASR model to distinguish between the different accents. Yeah.
Perfect. Thank you for the awesome presentation. You mentioned that adding the diacritics expected to improve the ASR model accuracy. By adding diacritics might make the recognition more challenging since each one will be considered as different symbol in the dictionary. Also, every similar word with different diacritics would be considered as different word and increase the dictionary, which may not have enough representation in the data.
Yeah, so adding diacritics is very helpful in the case that it will add more information about how we are pronouncing certain words. And yes, if we add diacritics, they are going to be considered as other parts of dictionary, especially if we are working with a backwater, because each shadda or dhamma is considered as a different character. And this is going to augment the vocabulary. It may augment the need of more computational resources, but especially if we are going to use more data set for this. But it could improve the results, yeah. So you have to choose between augmenting the data or the vocabulary size for a better performance, or keeping lower vocabulary for lower performance.
Okay, so next question. First, thank you for this amazing presentation. Then I want to ask you about the steps and some tips to create an ASR project.
I think we already talked about that during the demo and throughout the session.
Okay. Do you think extracting MFCC is enough as a feature to help with the ASR, or is it better to use multiple features?
So actually, we were using MFCC in the all the, let's say, architectures, not necessarily using deep neural network, but basically using statistical statistical models. But when adding the neural networks, especially when using the CNN model, the CNN architecture, it actually replaces this one, as it has the ability to extract useful features from the images.
Thank you. How do you segment words characters for the model input? And what DSP techniques have you tested besides FFT and Spectre?
Yeah, in our case, we worked on a character level, but yeah, for sure, you can use other segmentation techniques such as the SPE and WPE, word level segmentation, or subwords tokenization. But yeah, it could really improve the results. For example, the model that we showed in the last part is Citrinet. It works with the SPE and WPE and has shown really good performance when working on sub-token level.
Okay, next question. Thank you for this nice work. Do you think transfer learning from a standard Arabic model would be helpful to create a new model for some Arabic dialect?
I think it's a great question, actually, because yeah, it definitely could, and it is showing we are actually working on something similar, so it's showing great results. Yeah, the main idea is to take the encoder part, as when we pronounce words, we are actually pronouncing different characters, but the outputs or the vocabulary or the decoder parts would change. And when pronouncing words, there are a lot of similarities between the standard Arabic or the MSA between the dialectal. So the idea of using transfer learning from standard Arabic model to a dialectal model is a great idea. Even doing transfer learning from another language, even from English to Arabic, has proven great results. So yeah, definitely yes.
Thank you, Nourchene. So next question. DSP math takes a lot of time. What advice for beginner to get up and running quickly with ASR?
Yeah, you can basically start with the demo that we have shown right now. It will help you to understand the basic steps for building an ASR model, and then you can start improving the model architecture, adding some techniques like we have shown just now, adding the language model, and yeah.
Thank you, Abir. So last question. MFCC spec2 and MFCC coefficients are different. What are the best?
I didn't really get the question.
Yeah.
No. MFCC spec2 and MFCC coefficients are different. What are the best?
In what context? I didn't get the question.
Okay, so I don't think we have other questions. So thank you very much. Thank you, Abir and Nourchene. And let's take a break for 10 minutes, and we will be back with the third talk.
Thank you very much.
You can stay on the meet basically, and we'll be back in about 10 minutes. Thank you. Welcome back, everyone.
Welcome. Thank you, Zara. Welcome to everyone to our third talk, text-to-speech with TensorFlow. Our speakers who are with us, Amel, Sellami, and Khalil Rhouma from InstaDeep. Amel is a research engineer at InstaDeep, a Google developer expert in machine learning, officially a mentor at the Google for Startup in the Middle East and North Africa region, and was a host of the open-minded Ask Me Anything session. She was invited and sponsored by Facebook to take part in the F8 hackathon and conference. She is a volunteer speaker in various events like GTEx, Google for MENA, Deep Learning, and DABA. She has a software engineering background acquired from the National School of Computer Science, Annecy in Tunisia. Khalil Rhouma joined InstaDeep as an intern and then continued as an AI research engineer. He specializes in natural language processing by working on the latest advances in this field. Khalil is more focused on applying these technologies to the Arabic language to help boost the Arabic community for more digitalization. So welcome to Khalil and Amel, and the stage is yours.
Thank you, Khalid, for your intro. So just let me quick share. So I think screen share, right?
Yes, we can see it.
Okay. Thank you, Khalid, for the intro. Yes, as you said, we will introduce you today the text-to-speech with TensorFlow. Me, Khalil Rhouma, as an engineer from InstaDeep, and my colleague Amel Sellami as a research engineer from InstaDeep. Thank you for your attendance, and I hope that you'll satisfy from our presentation today. So starting with the outline, first we will begin with the introduction, and then we will speak about the TTS pipeline, how the TTS really works. And after that, we'll speak about the model evolution of TTS, and we will the timeline of the TTS model. And after that, we will list some challenges and next step in this field. Then we will speak about the TensorFlow, what's new in the TensorFlow and the updates. And finally, we will conclude the quick demo that will showcase our topic. So starting with introduction about the text-to-speech, which is also called speech synthesis abbreviation TTS. Actually, what is it is really the artificial production of the human voice. So, for example, giving this text in Arabic, Assalamu alaikum, the TTS model will convert this text into a wave format, and there is some measurement for the quality of this audio. The first is how natural it is audio, which means how it is close to the human speech, and the intelligibility, which means how it is understandable for us, how this audio it is understandable for humans. So this topic it is actually have some several use cases. It is originally designed for to help people with disabilities, especially the ones that have some visual difficulties. Lately, it is used in different sectors like transport, travel, and healthcare, advertising, and other sectors. And especially, it is used for the assistant like the AI, like the conversational AI and chatbots, and it is frequently used lately for these fields. So speaking about the TTS, so now we actually how do computers can process our voice? First of all, the sound signal is made by a variation in the air pressure. So this air pressure, we could measure this sound signal by measuring the intensity of this pressure, and actually it is a series of numbers that could illustrate our signal. For example, this is a shot of the real sound signal, which is the amplitude against time. So basically, this plot is made with 3 different frequencies. So if we want to plot these frequencies in a frequency domain, which means in an amplitude against a frequency plot in just a strict interval time, it's called spectrum. Spectrum could represent the same signal but in a frequency domain. And after that, if we want to vary the spectrum over time, we'll have the final spectrogram representation, which will give which will represent also our sound signal in another way, which is a frequency over time. And we could get information about the intensity and amplitude by the hue colors. So it is a 3D plot. And working with spectrogram is very beneficial because it is as an image that represents sound will be used with the CNN and will make very useful information about our sound. So speaking about frequency, actually the human does not perceive frequency in linear way. So the human ear does not perceive frequency in linear way, which means that we are more sensitive to difference between lower frequencies than the higher one. For example, taking this example, the two first frequencies, we could easily distinguish the difference between them. But if we want to move to a higher frequency, although it is the same difference between them, but we will hardly distinguish the difference between these two frequencies, which is to speak about the Mel spectrogram. The Mel spectrogram, it is a conversion made for the just normal spectrogram, which is a linear spectrogram, as you see. The number spectrogram, it is a linear spectrogram in terms of frequency. So the Mel spectrogram is conversion made by the Mel scale, so that the spectrogram will manage to deal with with the non-linearity of this frequency that we just spoke about, and it is tend to give more information and beneficial for the working with TTS models. So now we could, after speaking about the frequency and spectrogram, we could now move to the pipeline. So for our input, we have the text and audio, the corresponding audio of this text. We only need audio just during training. So we move this input and pass to our spectrogram model, where the spectrogram model will train and give as output a prediction of the spectrogram of the audio. After that, we'll move the spectrogram, the generated spectrogram, to another model called the vocoder. This vocoder is a generator of the final wave audio sample. So these two models are separately trained from each other. So for the first phase, which is the data preprocessing, we should have test the text from, especially from the foreign language words and extra spaces and other special characters, because it will impact our training and lead to some low performance for the generated audio. Also, it is better and recommended to use phonemes, because phoneme scripts tend to give more information about how the word really pronounce it. So it is highly recommended to use it instead of just raw text. Also, there are some quality checks that you could make for your dataset to have good performance and increase your model output performance. Like we should have a balance between audio clip duration and text length, because if we have too long text and with a very short clip, this will affect our training and will lead to very low performance in terms of audio quality. Also, we could measure the noise level in our audio clips and try to remove the noisy one, because TTS model tend to learn noise, and it is very and the noise could very easily impact our generated audio. Another thing, we could find the best audio processing parameters that fit our data, because we know the recorded data is differentiable from a speaker to another, from the male to a female. So we could tune these parameters to have a very good audio quality. And another thing, we could, for better audio processing, we could convert our audio to sample rate between 60 kHz and 20 kHz. After our data set, we could move the second phase, which is generating the spectrogram. So our spectrogram is a system composed of recurrent sequence-to-sequence prediction. And this network this network could map the character embedding and to generate Amel spectrogram. So because it is a sequence-to-sequence network, the encoder there is encoder and decoder. The encoder reads input character step by step and try to output status vector. After that, the decoder will get all these status vectors and will generate spectrogram frames step by step. So for the training goal for this phase, for the spectrogram model, the training goal is to achieve the best alignment possible between the encoder and decoder. This alignment will give an intuition about how well trained our model is. And if we get a clean alignment like this, it means that the model is well trained and could give a very clean audio and high performance audio samples. This is an example of the predicted spectrogram. But for example, if we have this this alignment, which as you see, that has some diffracted part, and the alignment is not clear at all. This is either it is just in the first steps of the training, or the model didn't fit well in our data and it is facing some problems dealing with the data. It may be caused by as we said, by the noise, or not the outlier in our data, or something. After generating the spectrogram model, now we could make our audio by in the first phase we could generate our audio by the vocoder model, which is, as I said, a trainable model. It is trained separately from the other one, from the spectrum model. So the goal is to convert the Amel spectrogram feature representation into time domain wave format and generate the final audio samples. These vocoder models exist in different architectures, such as with the convolutional network, neural network, with GAN, RNN, and others. So to test this model performance, we could just listen to the audio and try to see how natural it is. Try to listen if it includes some noise or robotic sounds, and and based on this criteria, we will know how the model will perform, how the model is performing in our data. Another thing I would mention, and I would take an idea for it, is it is that some environment are impractical or that does not support the Arabic text. So how could we use these? How we could face this? How we could solve this problem and make a TTS model from the Arabic text. And fortunately, there is a format called Backwater, which is developed to represent the Arabic script by just converting it to Latin script. For example, if we have this text, Assalamu alaikum, after conversion, we will get this Backwater conversion, and will easily represent the Arabic text. And the thing is, it is very easily to just adapt to our normal Arabic text without any issue or any problem. But if we have a diacritized text, if we have a text with tashkil, how we can solve this issue? Unfortunately, the Backwater it supports the diacritization, and will give another representation with more information for this text. And just to bring your attention, because this text will give us more information about how this word will be pronounced, and it is highly recommended to use this diacritized format, because it will increase the model performance and help the model to deal to know more about our language. So after that, now we could speak about some evolution for the TTS field. The TTS model starts from the 15 by the electronic devices, and then with some basic model like concatenate and format synthesized model, then some basic statistical model like Hatem based, and finally the deep learning based synthesized model. So we will look through some very the big point in this timeline. For example, we start with the concatenative TTS. The concatenative TTS is based on just concatenating the segments of recorded speech. So, for example, if we have this word hello and the phoneme script correspond to this word, and after that, if we just broke these phoneme and try to have some recordings for these separated phonemes. So now we have a database that contain separated small audio clip that refer to each phoneme. So if we combine these recorded videos, short videos, we could have this the word that we want, and we could generate our speech. This is just a basic example for with word, but in real life, the concatenative TTS has a very large database containing words and other stuff recorded. The bad thing is that for the drawbacks for this model, it is very time consuming, because have a large database and want to retrieve each small unit of sound recorded in the database. Also, it produces very low natural sound, and have a robotic sound in the generated speech. Another thing came up in the TTS timeline is the HMM-based speech synthesis, which is called also statistical or parametric synthesis, based on hidden Markov models. The idea is that this model try to learn and approximate the parameters that could make a speech. parameters such as fundamental frequency and spectrum, phoneme duration, and other stuff that could be as parameter that make speech. So after combining the model try to combine this parameter and process them so it can generate final speech. And after that, the deep learning based models come up with the WaveNet, which is one of the first deep learning based model for the TTS topic. Actually, it is a big event that happened in the TTS history, and it was created by the DeepMind Google's team in September 2016. So the WaveNet, it is a deep learning model based on the convolutional neural networks. It requires it doesn't just work with just raw text, because it needs some extra and some intermediate pre-processing from its front end. So it works with linguistic features, not just raw text. So after giving these linguistic features to the model will try to learn and produce the predicted voice with the real audio form. So what this model have actually the benefit of this model that is produce some much more natural sounding speech in compared to the previous statistical and simple models. So the training, as I said, giving simple just 1 second of raw of audio clip and some linguistic features, the model will be conditioning on this feature and try to predict the audio sample. Actually, try to predict each point, each symbol in this waveform. So after that, some models were inspired from this WaveNet model, like the Tectron, which is a spectrogram generator model. And this model was built with the sequence-to-sequence network with attention. It gets as input text and audio pair, and try to and train it from scratch. So this model, after training, it tried to map the character into map the character into spectrogram frames. And the spectrogram here was just a linear spectrogram, not female one. So and after this Tectron model, Tectron 2 based on this model was built, because they have some they made some changes to the architecture of Tectron model and some improvements. Also, this model was trained trained with speech and its corresponding transcripts. The audio and the text, corresponding text. The improvement was made in the layer hidden in the layer of the model. The benefit also of this model is that to predict the male spectrogram, it works with recorder, which means we can give this spectrogram as input to the recorder model. In our case, they used the WaveNet. We saw previously they used the WaveNet recorder model, which will convert the spectrogram into wave sample. Another thing, we could use these Amel spectrogram with the Griffin algorithm. This algorithm will produce an audio sample from the spectrogram. So now we could list some challenges and next steps in this TTS field. For example, the difficulties with some words that not seen before. Even the deep learning based model make a big leap and big change in the TTS history, but we still face some difficulties with the non-seen words and the difficult words in our data. Also, there is some difficulty of including the vocal expression, like if it is someone happy or sad or mad. This is still a challenging task, and even for the deep learning based model, so it's still under research. Also, these type of model, especially the Takatron tool, it is very, very heavy model. So we still cannot yet generate the audio in real time because it has some very, very heavy model and have many billion parameters. Another thing, speaking about the end-to-end TTS model, we didn't yet, we still haven't yet any end-to-end model that generate an audio directly from the text, not with some other model components. And another topic, another issue in TTS topic is the code switching or language alternative. So, for example, for the spoken English words, there are some French words that included in the text, in English text, when people spoke English. So how the model will learn these French words and try to process as a French word, so it have to pronounce it as a native French, not an English words. And now I could pass the word to my colleague Amel to continue the presentation.
Great. Thank you, Khalil, very much. I will try to share my screen from here. Okay. Okay, I hope everyone is able to see this. Assalamu alaikum الناس الكل. I will try to talk few in Arabic, sometimes few in Arabic and sometimes in English. I hope you can hear my voice. إن شاء الله الكونكشن ما تقصش. So just a quick overview يعني in a general manner. I think one of the most important things nowadays in natural language processing is trying to understand the different parts that we can use in an application. يعني الهدف في الآخر هو how to create an end-to-end application using natural language processing. يعني في معالجة اللغة الطبيعية there are different types. The first part that Hatem and Malek talked about هو the part related to sentiment analysis. It can be in Tunisian dialect, using transformers and all these kind of things. The second part was talking about ASR, which is basically trying automatic speech recognition. يعني لدينا يعني we have an audio, لدينا audio, and we try to generate the text of it. It's like understanding. It's like people when they chat. And the second one is the one that we are trying to present to you today, Khalil and I, which is basically having an audio and having a text actually, and we're trying to generate an audio. يعني we have the text, and from this text we're trying to generate an audio or a spectrogram. And this is basically the whole idea of this TensorFlow Meetup, as I want to try to sum it up. Okay. الشيء المهم يعني because it's TensorFlow, of course, one of the most important things to talk about, of course, is TensorFlow. So what's new with TensorFlow in 2021? هو في الحقيقة ما يوجد هنا هو كله موجود في الجوجل I/O. It's part of the Google I/O introduction. So you can find all this detail online. يعني there is nothing that we can add about it. الشيء المهم هو إنه TensorFlow when is used actually there is different parts. The first part is that TensorFlow is more used for production. يعني نستعمل TensorFlow because there are different kind of models that are being used, and we have like different kind of architectures that can be later on يعني نستعملوهم في production. And when we talk about production, like applications, هو في الحقيقة nowadays in these times we use it every day. We use it on Facebook, we use it with Twitter, we use it like I don't know, everywhere there is AI, and everywhere there is like models that are put into production, and this is the goal actually, I think. So basically one of the TensorFlow's important things is that, okay, let me try to put the cursor. Okay, one of the TensorFlow important major, let's say, difference between TensorFlow 1.0 and TensorFlow 2 is that having all the APIs together. يعني قبل when we talk about TensorFlow 1.0, there was like different bunch of APIs. يعني different APIs مثل الcontrib, slim, executors, estimators, and all these kind, and Keras, of course. And it was very hard to have a global vision on which model or which API to use for production. So one of the things that made a huge leap in TensorFlow 2.0, it's like making things easier for Python developers using Keras. So the major improvement is that Keras was like invented, or let's say created by François Collet. And it was like, and he outsourced it in the for the community. And in this part, 2.0 was created, using Keras. The difference between all these kind of models is that all of them, like the difference between all this kind of version is that the first one was easier, having easier Python developer for making it easy. The second one is supporting TPUs and all these kind of things. The 2.2 profiling tools, adding profiling management. Yani, when you have different models and you try to find the best one, the best hyperparameters and all these kind of things related to it. Bader, the 2.3 had better data management improvements, 2.4 updating the distribution of training using parallel GPUs and all these kind of details, and 2.5 is like adding quality and stability. And حين نتحدث عن quality نتحدث عن using research, يعني improving the research in the communities with TensorFlow. Okay, so what's the major important, as I think, announcements that Google was done by Google at Google I/O is like the first one is TAFE extended, which is basically you have like a platform. It's a paid platform, it's not free. And this platform is used for production ML enterprise at scale. So you can have like bug fixing issues, can be helping in bug fixing issues, can be helping giving you Google Cloud profiling platforms and all this kind of details that can help leverage your production using Google with TensorFlow extended. The second thing, and I think one of these things is that it's responsible AI. يعني حين نتحدث عن responsible AI, and I think in Tunisia we don't talk enough about it. And responsible AI, meaning that you first need to know what's in your data. There is like something called know your data, and it means like the bias. يعني الbias, the gender can be gender bias, يعني female, male, and all these kind of things. والشيء الثاني هو يعني having APIs that help you understand how much your model is private, for example. يعني the privacy part, the fairness part, how fair is this? يعني حين نتحدث عن يعني putting a model in a production, يعني putting a model in real life, it's not an easy thing. And we have always experienced some kind of weird, like for example, Facebook telling you that this is very harmful or something like that. And this is part of the responsible AI kind of thing, and which is really important to know and understand. The last part is TensorFlow for mobile and web, which is basically trying to say we have like the TensorFlow Lite runtime will be bundled with Google Play services. يعني قبل يعني before one of the things that were being able or was there is that you have to add the runtime, the TensorFlow Lite runtime before putting your application into Google Play. It's not the case anymore because Google Play provides it for you. So it makes like having a low size kind of applications for your model if you want to have a model which is for production. And the second one is that you can now run TensorFlow Lite models on the web directly. There is a bunch of APIs, the TensorFlow Lite models, and that you can use with TensorFlow JS or something like that. And it's really interesting in a sense that it can help like in different kind of things. Let's try to go to the demo, which is the last part of our talk today. I hope you are still able to hear me. Okay. This was taken from the TensorFlow TTS kind of GitHub. So everything you can find it in the audio samples. There's also a very basic Korean collab version if you want to try it out. So all you have to do is go to TensorSpeech, GitHub, IO, TensorFlow TTS. One of the models that was implemented and developed by Google. Okay. When we talk about TensorSpeech or TensorFlow TTS, which is it's a real-time state-of-the-art speech synthesis, which is a Tachytron application. It has like different architectures, Tachytron 2, Melgan, multi-band Melgan, fast speech 2. We'll try to see these different models and in a very easy way. سنحاول أن نفهم ما هو الفرق ما بين هذه النماذج. And we can speed up the training and inference process, and we will see an example in English. So it won't be in Arabic, but it will be in English, and I think it's really interesting to see the results of putting and the results out of it in a bunch. Okay. ما هو البروسيس أو كيف يحدث the training pipeline. مثل ما تحدث خليل سابقا. First we have a model which is used to generate a Mel spectrogram from text. And there is so the first part is that we have a text, and then we try to generate a Mel spectrogram from it. The second part is that from this Mel spectrogram we're trying to generate the audio. لدينا we do have two stages, and at the end-to-end approach to this is the end-to-end approach to generate audio from text. So it's like 2 times. Not directly, which is still under research, as Khalil talked before. I think the concatenative TTS part, as Khalil talked about it, which is like relies on highly quality audio clips recording, which exists in research right now, and the different kind of 2 phases that it has. And then I think it's the first part when we were trying to create or to generate concatenative like TensorFlow TTS generative speech, and the highs or the pros is that it gives high quality and the possibility to preserve the original actor's voice, and the cons is that it's time consuming. There is the pipeline of trying to find the features in a way is very time consuming. The second part هو في البروسيس in this whole process هو إنه we have also the parametric TTS, which is basically the goal is to address the limitation of the concatenative TTS as using statistical approaches like the hidden Markov chain, the hidden Markov's model, sorry. Which is basically you have a first step, which is the text is processed to extract linguistic features, and the second step is to requires extraction of vocoder features. When we talk about vocoder was the second part of our process. So the first part is generating a spectrogram with the model, and the second part we generate from the spectrogram an audio, and this model we call it a vocoder or something like that, vocoder models. Pros, it's that it increases naturalness. The voice or results looks natural and not robotic. The problem with generating speech is that most of them sounds like it's like a robot talking, which is very hard to avoid at the first early stages, for example. And the second, so what's the best part of having of parametric like TTS with, for example, HMM? It's like increasing the naturalness. The cons is that we have a lower quality of audio and the voice can sound very robotic in a way. Okay, and Okay, so we said there are three types. The first part is the concatenative. The second part is the parametric models, and then there was like the using deep learning models to generate to extract the features from the text that we have. First of all, is like a very basic approach. Yani, first of all, what we try to do is to install everything. Yani, we import the system, we clone the GitHub tensor speech, and then we add it to our path, which is already done. And then we install actually the German transliterate. This is a bug actually from their side because they have a bunch of German like models that they can use, that you can use to for example, for German, Chinese, or anything else. But this was for the German transliterate is used for German, and you have to install it if you want to use the tensors TTS, and then we import the #5 PY version for our checkpoints. Okay. الجول of this يعني الدemo هو to see the difference between the different models that we have, the tachytrons, fast speech 2, and the different vocoders. يعني Melgan, everything, all of them, all the vocoders will be based on the Melgan. Sorry about this. All of them will be based on the Melgan, and there is different kind of let's say versions of this Melgan part, and which is the vocoder part, and we will listen together to it. Okay. So basically what we do is everything is all these models were already pre-trained, and all we gotta do is doing inference. Yani we're going to test these models that was already trained on English in our case. So if we try to explain in a nutshell ما هو الملجان. الملجان هو non-autogressive feed-forward convolution architecture. So it has a very basic convolution architecture. You have the mass spectrogram. So we're talking about the vocoder, which is the second part, right? If you're still with me. So basically we have a mass spectrogram, we have convolution layers, and then we try to do an input sequence, which is basically dilated convolution blocks, and then we get our results. So this is the basic architecture of the generator. The discriminator part is just basically you have a raw waveform, and we try to do a discriminator block, and then you get some features, feature maps plus output, and then you average pool these results. يعني الملجان هو, as the name says, it's a GAN architecture. يعني this generative adversarial network architecture. Well, generative adversarial network, I'm not sure if you're familiar with it or not. It uses two types of models. يعني we have two models. الموديل الأول هو يستعمل which is called a generator. It generates in this case spectrograms. It can be, for example, in images. It generates images to try to fool, يعني fooling the discriminator. And this discriminators try to will be fed. يعني we will give him the generator's output and the real data that we have, and we try to train the model in a way that the generator fools the discriminator. In a nutshell, what's GAN? And when we say non-autoregressive, it means that the decoder part generates everything not simultaneously in a way or in another. And this is a very basic bunch of about the Melgan architecture. الأشياء اللي we need to also import هم ال TensorFlow as TF and Matplotlib to see to display all the results, and we will use the TensorFlow TTS inference part to do the inference using this model. يعني the Melgan will be used as a vocoder for the second step. The first step, as we talked about it before, tag control 2, we will then import it. And I think Khalil talked about it, so I will skip this part to have more part for the questions. The second model that we will use is called fast speech, which is if we try to understand what's fast speech in a nutshell, يعني هو it's a neural network based on end-to-end text-to-speech. الجول متاعه هو إنه these models are يعني parametric approaches neural network based end-to-end models suffer from slow inference speed. يعني when you're going to do the testing and you want something which is real time, there is a slow inference speed, and the synthesis speed is usually not robust. It means that some words can be skipped, ولا repeated, ولا lack of controllability, which is like voice speed. Can we يعني speed or have a speedy voice or not, and the porosity control. This work, this is their basic abstract actually from the fat speech paper, which is basically they propose a feed-forward network based on transformers. So basically they use transformer for getting the attention, the most important part in your speech, in your text or something like that, to generate Mel spectrograms in parallel, meaning that you don't have to go all the way to the whole, you see the whole speech to be able to generate the result, which is the parallel, and that's the non-autogressive result. And then there is also, which is basically, so basically they extract the attention alignments from the encoder decoder. I think you have seen the attention kind of line alignment that you have that Khalil have talked about in the presentation, and this is part from the encoder-decoder based teacher model. So we have a teacher model for phoneme durations prediction, which is used by a length regulator to expand the source phoneme sequence to match the length of the target Mel spectrogram sequence, and all of this for a parallel Mel spectrogram generation. So the results is that it speeds up the Mel spectrogram generation by 270 times, which is really important and really interesting for getting the, trying everything out in a more speedy way. Fast speech 2 is an improvement to fast speech, which is basically you have like teacher, student. It uses actually a technique which is basically used really this much in nowadays, which is called self-supervised learning, which is basically you have a teacher-student distillation pipeline. And yeah, so basically this is for fast speech, and this is one of the disadvantages, because the teacher-student distillation pipeline is complicated and time-consuming, and the duration extracted from the teacher model is not accurate enough, and the target Mel spectrograms distillated from the teacher model suffer from information loss due to data simplification, وإلا both of which limit the voice quality. Fast speech 2 is actually try to solve too many mapping problems by using actually training the model with ground truth targets instead of simplified output from the teacher, and then introducing more variation information like speech, energy, and more accurate duration as conditioned inputs. And yeah, this is just the experiments results. It shows that it achieves 3 times training speed over fast speech. Fast speech 2 also have better, faster inference speed, and it outperforms fast speech in voice quality and can even surpass the autoregressive models that only have to do the decoding part one by one, not in parallel. Okay, so this is the Melgan original. There is different Melgans there is the Malgan STFT, which is basically Fourier transformer kind of loss that they use to improve the results. And then there is the multiband Malgan. I will not go into the technical details because we're running out of time. I'm sorry about this. But if we try to see the inference of the results, what we try to do is we try to generate or to do the synthesis, basically using Tacotron Fast Speech 2. These are the only models that this notebook uses. And we can see, for example, for the vocoder part, the second part that we talked about, using the Malgan, for example, the first one, Malgan, or multi-band Malgan, or the Malgan SFT. Okay. After all of this, what we got to do is, for example, this is the Tacotron True plus Malgan, and this is the kind of the results. As you can see, the alignment, the attention alignment is quite good, but there are some parts which are very lacking. And if we try to hear, I hope you can hear me.
We can hear you fine.
You can hear me? You can hear it or not?
Yes.
Sorry?
No, wait. Can you click on play, actually?
Okay. You can't, right?
We can't. You should have a button at the top of your video to allow the system audio.
Okay. You can, I hope you can hear it right now. So basically, just to make sure, this is the text that we're trying to generate. So it's basically Bill get into the habit of asking himself if this is thought true, and if he wasn't absolutely certain it was, he just let it go. And this is the input text, and now you can hear the result.
Bill got in the habit of asking himself, is that thought true? And if he wasn't absolutely certain it was, he just let it go.
As you can hear right now, it's just like, it's a good result, but as you can see, in this part of alignment, there's kind of some robotic kind of sound, and this is due to this kind of not very great alignment. Okay, let's try Tacotron True plus the Malgan STFT.
Asking himself, is that thought true? Bill got in the habit of asking himself, is that thought true? And if he wasn't absolutely certain it was, he just let it go.
Okay, and we can see that using the Malgan improved the results. Okay, and then there is the Tacotron True plus multiband GAN.
Bill got in the habit of asking himself, is that thought true? And if he wasn't absolutely certain it was, he just let it go.
Okay, I think I will try to only use the fast speech Malgan.
Bill got in the habit of asking himself, is that thought true? And if he wasn't absolutely certain it was, he just let it go.
The most important part is that even the speech understand the intonation. You will get this at the end. Some models does not get the right intonation in when speaking, but some models like Fast Speech 2 with Malgan will get really good.
Bill got in the habit of asking himself, is that thought true? And if he wasn't absolutely certain it was, he just let it go.
So sometimes it just stops and then continues. It's like another sentence.
Bill got in the habit of asking himself, is that thought true? And if he wasn't absolutely certain it was, he just let it go.
Okay, and the last part is that the fast speech 2. I hope
Bill got in the habit of asking himself, is that thought true? And if he wasn't absolutely certain it was, he just let it go.
You can hear, like in this one, fast speech 2 plus multiband Malgan, is that how perfect it gives the intonation about each part when talking in English. The sound seems really good compared to the Tacotron or fast speech, and it's not robotic. Sometimes it sounds robotic for Tacotron 2 or for fast speech. Right now, it's really it gives really good results. Okay, let's try it.
Bill got in the habit of asking himself, is that thought true? And if he wasn't absolutely certain it was, He just let it go.
Okay, and the last one is the past true plus Melgan.
Bill got in the habit of asking himself, is that thought true? And if he wasn't absolutely certain it was, he just let it go.
And this is kind of the difference between the different model. I mean, fast speech 2 gives really great results compared to Tacotron 2 when it comes to not having I mean the not having that robotic kind of result, or not sounding like very robotic. It sounds like very human, and it gets the intonation, as I said, like very perfectly. Some of the models stop in the middle, for example, of the sentence, because it, like, for example, and if it wasn't absolutely certain it was, and it stops, and then it just let it go. And some of the other models just carries on to say it in a non very human way. Yeah, I'm not sure if you have any kind of questions, but I think this is just what we wanted to try to show you. I know it's not in Arabic. We're sorry about that. But unfortunately, we cannot share for now the Arabic part that we have worked on. And yeah, I think I will stop sharing my screen. Cool.
Thank you very much. So we have a question. So what's the hardware used for Melgans?
Typically, a 1 T4 GPU can be enough. Yeah. Khalil, if you want to add something on it.
Yes, that's it. Yes.
Okay. A T4, 1 GPU T4 you can work on it, but it takes I think it needs like 1 T4 with 16, I think, gigabytes. So something like that.
Okay, nice. So Amel is asking, it's not clear which approach, Fast Speech 2 or Tacotron 2 is better. Can you please comment what is the current TTS state of the art?
So basically, if you try to see the models that we have shared, the results, all of them gives really good results, as we have shared in the notebook. But the Fast Speech 2 can gives very it's a lot more easier to because it has the parallel kind of the results. And I think Fast Speech 2 is the state of the art related to the training, right, Khalil?
Yes.
Yeah, Fast Speech 2 is the right now the state of the art for generating good quality audios, and you can hear it as we showcased it in the notebook. So basically, Tacotron 2 sometimes can be very very hard to yeah.
Yes, sometimes have some robotic sound, but Fast Speech to give more clear and natural sound compared to Tacotron 2.
Yeah.
Okay, thank you. So can you share the notebook link with the attendees?
Yes, sure.
Okay. Thank you very much.
To share it here. You're welcome.
Thank you, Amel, and thank you, Khalil, for this session. It was clear and very good. Thank you. So finally, we come to an end with our last talk with Karim Beguir from InstaDeep. Karim is the CEO and co-founder of InstaDeep, as a graduate of France École Polytechnique and former program fellow at New York University's Courant Institute. Karim has a passion for teaching and using applied mathematics. He is also a Google developer expert and a mentor at Google for Startups Accelerator, and is a steering committee member of Deep Learning in DABA. Welcome, Karim.
Hi, Khalid. Thank you for having me. It's a pleasure to be here.
Our pleasure is yours. So you will be talking about AI language models' latest developments. The stage is yours.
Absolutely. And please tell me if you see my screen in present mode.
Yeah, it's working fine.
Perfect. Well, first, it's a pleasure to be here, and we're very excited that this TensorFlow Meetup Tunis is happening, and hopefully there will be many more of those. We're also excited that it's a diverse team of talents from InstaDeep, from iCompass, and other volunteers as well. So this is really great, and this is really we believe the future for the ecosystem in Tunisia when it comes to AI. And today you've had different sessions about language modeling and very interesting discussions about practicals. I wanted to share with you sort of my perspective about what's happening in language models, why you should be paying attention beyond the examples discussed today. So it's probably a less sort of programming, but more like mathematical and sort of overview, but still thought it was important to get you a sense. So first, I mean, when we're talking language models, here we're really talking about attention-based models and transformers. And as probably all of you should know by now, transformers is a sort of a revolution because you're not processing sequences, for example, NLP, just sequentially like we used to do it for LSTMs or more generally like recurrent neural networks. If you see here on my screen, for example, like dependency between, the hidden layer T for a large T and X0, like the initial input token here is quite long and grows longer with the sequence length. And what transformers have changed is the fact that now you're actually looking at something where you have the same amount of interaction, I would say, between the different tokens, no matter where they are in the sentence. For example, if you take this English sentence, the animal didn't cross the street because it was too tired. And really, like if you look at the dependency of it, you see that there is a strong link with the animal here, which is highlighted in a darker color. And that is super interesting because you're directly modeling sort of the interaction and putting the weights where they are from a purely data-driven way. So transformers were created in 2017, but it's really over the last, I would say, 2 years that we've seen like incredible, innovation and speed and scaling along these. And so what's the idea here? This is sort of like, if you have to remember something from this presentation, that would be probably it. The idea is like, you probably heard that software is eating the world, right? And it's probably one of the reasons why you're in this session today. And this was from Mark Anderson from Anderson Horowitz in Silicon Valley. Then we had deep learning is eating software, which was popularized by Andrej Karpathy, notably the director of AI at Tesla. And what I would like to tell you, and it's sort of my own take on it, is that after deep learning eating software, now you have transformers eating deep learning itself. So if you have the world here, its software is eating it, deep learning is eating software, but then transformer is eating deep learning. So that's kind of important when you think about it, that you should be very familiar with what's going on transformers. And I hope you enjoyed the previous sessions where you had several examples of work done, especially for modeling Arabic language, but also speech, like we just saw with Amel. And so this is really a very powerful technology. And what's super interesting from my perspective is transformers emerged in the context of NLP, and this is why we call it language modeling. But the amazing thing that we've seen over the last 6-9 months is that now it is starting to eat other deep learning models. And this is why we say transformers are eating deep learning. So if you look, for example, at convolutional neural networks, which were sort of like the mainstay of AI vision for a very long time. Yann LeCun from Facebook AI invented CNNs in the late 80s. And they've been like powering the whole AI vision revolution until very recently, where you had this transformational paper, An Image is Worth 16 by 16 Words by Google AI, which effectively mentioned and explained that you could actually train transformers on images, on pixels, seeing basically cutting pixels effectively, either 16 by 16 or another type of dimension. But the idea is you cut your whole pixel image in batches, and then you build relationship between those. And that is revolutionary for multiple reasons. First, because the VIT model, like the Vision Transformer model by the authors, actually got very good results. So it's a technology that works. So only for that, you should pay attention. But what's more interesting is that now with this technology, you can actually link multiple modalities. So in the example below with this picture of a surfer, you could build a basically relationship between text that describes the image and the image itself pretty much directly with attention. Exactly like if we come back here, we had it depending on and related and pointing to the animal. Well, you have the same idea here, like the person, where is the person? Well, you see you have higher dependency here, riding, etc. So you could surfboard here, you see it's lighting up these patches here. So the idea is that you're directly modeling pairwise interactions. And this could go beyond simple pixels or simple text. It could be text and vision, or it could be text and vision and speech, like you just saw with Amel, that speech also works pretty well. So that's the idea here, is this is powerful. And in this particular case, transformers and attention-based models are now becoming very competitive in vision tasks. And when you think about it, this was not something obvious, because CNNs have been used on the notion of translation invariances and other invariances which are based on like visual tasks and visual priors that the human designers put into them. Transformers don't have that. In a sense, it's a more general prior. It's the notion of, okay, I'm gonna have different parts or different tokens interact and sort of measure their interaction directly by data, and yet it is competitive on vision. So in general, like when a speech, I'd say an AI technology like AI becomes very powerful and very big, you tend to see specialization. You tend to see, for example, like, speech going with LSTMs, vision going with CNNs. And it's very rare that the technology comes and unifies the field again, the field which gotten much bigger and much more like specialized. And this is exactly what happened with transformers. So that is super interesting. And indeed, you can also see that transformers and language models are also eating biology. Because if you look at biology and proteins, which are basically the macromolecular enzymes that are powering life, they're based on sequences, amino acid sequences, and 20 of them. And those sequences directly create shapes, whether alpha helix or beta sheets, that create ultimately a 3D structure that is going to drive the function of proteins in your body, whether it's for energy, energy generation, or for movement with muscles and others. And the idea here is the same way we created dependencies between tokens in a sequence, like we saw before. You could actually create dependencies on the different amino acids. Effectively, proteins is a language made by 20 amino acids, so there's only like 20 different tokens, but the relationships they create are quite complex. You see here in interactions between these different amino acids creating hydrogen bonds and other interactions here. And so if you take this and do it at a very large scale, if you build attention models at a very large scale, what you get ultimately is the biggest scientific breakthrough of the last year, which is what DeepMind did with AlphaFold 2, basically a system that goes from sequence alone through the use of transformers and attention at a very large scale, purely data-driven in many ways, and get you exactly to understand and predict the shape of proteins. So you don't need to understand the detail of what's going on here, except that the color is actually the prediction here in this one, and here the other color is the experimental result, and you see that they fit almost perfectly. And on a scoring, this is the GASP competition. You see AlphaFold 2 here literally smashed everything. So why am I showing you this, and why is this important? It's important because it shows you that a general purpose technology such as transformers and language model can actually go and beat ultra specialized teams and technologies, in this particular case in biology and biophysics, by a very large margin. So in a sense, if you master technologies such as language models, attention-based models, well, you have a tool which is extraordinarily powerful. And I hope you understand why now we're saying that transformers are eating deep learning, and deep learning itself is the new software. So I wanted to sort of attract your attention now on why in particular this is happening. This is happening because language models scale very, very well. There is a paper from OpenAI, which is one of my favorites. So for the people who are at InstaDeep, they probably saw this because it's one of my favorite papers. Not a super recent paper, but a very important one from OpenAI, where they literally went and studied the scaling properties of transformers. And so I'm just giving you like the key ideas here. The idea is that first, when you have a model and you're looking at a particular problem and you're trying to reduce test loss, ultimately test loss is a function of compute, data, and parameter size. You tell me, okay, well, did I really need to know this again? It's kind of obvious. Well, I'll tell you something that's not obvious. It's the fact that it's actually a power law. It's pretty amazing here, like the fit you get, and this is like experimental fitting to like doing all the experiments and fitting like empirically what you see. You have like almost perfect power laws. That is interesting. So in a sense, you can predict what is going to happen if you put in more compute, add more data, or add more parameters. And to this point, you can actually get the test loss to be a direct function empirically of parameter size and data. I mean, if you think about it, like for most of us in machine learning, it's the notion of, okay, I'm going to reduce the loss. It's pretty much like, okay, will I get to a good result or not? But the notion that the loss itself could actually be a quantifiable function of inputs such as model parameters and dataset size, that is super interesting. And you can directly extract from this very sort of usable insights. For example, if you increase your parameter size by 8x, you know that at some point, the data, you might overfit the data, but where are the critical thresholds? And you see here that ideally, if you increase 8x parameter size, you should be increasing data 5x. And so you are capable actually to understand what's happening in your model and derive some things which might be not very intuitive, such as insights such as, for example, if you have a larger model, you're actually going to get to good results faster than if you have a smaller model. You might think, I mean, at least me, sometimes I thought that, well, if I have a larger model, I need to feed it a lot of data, and okay, it's going to get me to a good result, but I might need to feed it a lot of data to get to a very good result. Well, that's not true, actually. And if you see here, by the number of tokens processed, if you have a given number of tokens, if I block myself here at 1 billion tokens, for example, well, you're going to see that basically the larger model has a much better loss for the same amount of tokens processed than the smaller model. This is true actually at any number of tokens processed. So you might say, okay, but that's just due to compute. You have more compute because to run a model like this, you need a lot more compute. Well, that's actually not true. Like if you have a given compute budget, it's better to have a larger model. Yes, it's going to run on less epochs. It might not converge, but it's still going to get you better results. And by better results, I mean better test loss for a given test loss objective, or let's say a given compute budget. So imagine this, you have a compute budget. You're wondering, like, should I train a smaller model for a very long time, or should I train a bigger model? And even though I don't reach convergence, like meaning that the test loss doesn't plateau or goes back up, well, it's actually better to have a larger model. So, and again, you can quantify those relationships. So my point here is that machine learning with transformers unifies the field, but it's also making it more scientific, if I may say, and scientific more in the sense of physics, not mathematics, because these are empirical laws, but yet they are quite important. then they will explain to you, for example, I mean, some of the work we do can be quite compute intensive. For example, the collaboration we did between InstaDeep and iCompass to create TuneBERT, which we just open sourced for the community. Well, that required a significant amount of effort and decent amount of compute as well, not massive compute like, you know, like the tech giants like Google or Facebook, but still a very significant amount of compute. So you have to be more scientific about the way you design your experiments, and importantly, understand that if you're going to dedicate more compute, how should you, relatively speaking, grow your model size, your batch size, the number of epochs, for example, that you're going to be doing on a particular training. And it turns out that for NLP and transformers, you have pretty stable relationships. And the interesting one is that you better grow the model size in relative terms much more than the batch size and much more than increasing the number of epochs. These are kind of insights which are not obvious. When we tell you this after the fact, it might seem obvious, but it really wasn't. And this is important because it allows you to sort of plan ahead and say, okay, if I'm going to dedicate, I don't know, you know, in a large experiment, 1 petaflop day of compute budget, well, where is this likely to get me in test loss, and how should I allocate optimally model size, batch size, and serial and amounts of epochs? And when you think about it, this is exactly what OpenAI did. I'm sure all of you are familiar with GPT-3, which came in from OpenAI pretty much a year ago, and which was gigantic, or say gigantic for at the time, with 175 billion training data, which was just massive, with 400 billion word tokens taken from internet and all the encyclopedia of the world, and etc. And you see that GPT-3 starts to become so good that it will confuse. And here, this is basically humans' accuracy at detecting GPT-3 versus real news articles. And you see that it's sort of converging to 50%. When the model, the transformer model, gets bigger and bigger, 50% means that, you know, you're not better than a monkey at guessing whether this is AI or this is actually real news article. And this is actually an example that I find pretty fascinating, totally generated by GPT-3, about some vague story about United Methodists agreeing to a historic split. I would challenge you that if you show this to someone who doesn't know context, that to guess that this is AI. And we sort of played this game you know, with a few people at InstaDeep, where we were showing like some text and some speech in chat on Slack, and people could not guess, is it like somebody real speaking, or is it like GPT-3? So again, this shows you the power of scaling transformers. And maybe like we don't have too much time, but I just want to say a few words about the fact that research is continuing to advance extremely quick. And now you have new technologies that are coming in, new insights, and particularly from Google, which is, you know, one of the very best, if not the best team in the world when it comes to AI research. And Switch Transformer, which came in early this year, is pretty remarkable, because until now, what I've shown you is effectively, if I'm going to scale the number of parameters, I'm going to scale compute budget pretty much accordingly. But that doesn't need to be true. Like, you could actually scale the number of parameters, get to 1 trillion parameter, and still be quite compute efficient. So how does this work, and how does this accelerate transformers? Well, it's the notion that, you know, when you're looking here at your self-attention layer, you have a feed-forward layer, which is usually here. And what you're doing in this particular case is, rather than having a classic feed-forward, and where you're taking basically your whole hidden dimension and pushing it further, well, you're going to have different feed-forwards or different experts, and you have a routing system that's going to say, okay, in this particular case, based on those embeddings, I'm going to route and use feed-forward, like network number 2, and etc. So you could get like hundreds of experts this way, and a much bigger like much bigger model. In the paper, actually, Google goes up to 1.6 trillion. And to my knowledge, you know, like the best AI models at the moment are around these. The Chinese have done something similar on Chinese language as well. But what is interesting here is that when you are actually going to at inference time, you're going to go only through one of those layers here. So that means that you are not less efficient or bigger from a compute budget than a classic transformer. So for the same flops budget, you can actually infer at the same speed. The only difference is now that your model is much bigger and has a lot more parameter diversity. And indeed, it gets better efficiency when you are doing training and training speedups. This is super interesting because now we are in the world of trillion parameter models, but efficient models. And so this at a smaller scale can apply to the work all of us do, meaning that, you know, those are models that can be richer in terms of acquiring pattern, but not more expensive to deploy at test time. So I think in particular, this model is super exciting. And when you think about multimodality with it, and also all the progress which is happening in self-supervised, you see that there is really a framework where transformer models, ranking in even, much more than trillion parameter models. I would imagine that this is going to grow, continue to grow very quickly, are going to get to a point where they absorb data at a scale and efficiency where the results are going to be nothing short of remarkable. So I'll stop here, and just to conclude and take some questions. If you were to remember something from this presentation, well, remember that transformers are eating deep learning, or language models are eating deep learning. So it's a very good time to learn more and get familiar with those models. In a sense, probably the best investment you might make. If it was like 4 or 5 years ago, you would have needed to learn about LSTMs, RNNs, and CNNs. Well, here you don't have to. You just learn transformers, and you have something that's going to work, and attention-based models are going to work for pretty much everything you can do. Those models scale very well, and we haven't reached their limits yet, but importantly, those sort of behavior can be quantified in a remarkable degree of empirical accuracy, I would say. And now with more efficient use of compute for the number of parameters of your model, with multimodality and, of course, the revolution in self-supervised learning, which we will keep for another day, and that's a whole subject on itself, you're getting at a point where someone who is passionate about learning and deploying this type of technologies can really reach new breakthroughs. I hope the work that the InstaDeep and iCompass teams did on Tunbird inspired you to dig further, use the open sourcing technology that we had, also use the open source tools that you have on TensorFlow Hub. The link is here. But this is a fast-moving world where you can really make a difference. And it's never been a more exciting time to be learning about AI, using AI, and innovating with AI. So thanks a lot for listening to the presentation. And I'm happy to take questions from here.
Thank you, Karim. So we have a question. Attention mechanisms seem to be central to the success of transformers, NLP, CV, time series, etc. Is there any intuitive explanation for this? For example, hidden layers are what enabled universal approximations in neural networks. Do you think something similar is happening with attention mechanisms?
I think I'll give you my intuition about what's happening with attention. Attention is a sort of a universal computational engine, primitive. That's how I would say. So what do I mean by this? Is that the world is driven by computation, and attention is just an efficient way to model that computation and provide rich enough computation to capture the behavior that you're looking for. There is a super interesting paper actually that came recently by Peter Abir and some colleagues in I think University of Berkeley, that says transformers are universal computational engines. What does it mean? It means that if I take something like GPT-3, okay, it's been trained on English for NLP, and that's it. Imagine I freeze GPT-3 and I want to train for Arabic or anything else, or for proteins in biology. I just change my input. So I'm going to need an encoder layer, obviously, because you're going to feed, basically embedding. So you just need to change the embedding layer. And let's assume I just change the final feed forward layer of my network to get to the and reshape to the output I want for my problem. I freeze GPT-3 in between. Well, what do you think is going to happen? Well, the amazing thing is that actually it works very, very well, and you don't have to retrain a lot. So effectively, attention mechanisms are sort of universal, and they could be trained for something that has nothing to do with the problem you're looking at and frozen. So all the attention layers are frozen. You're just changing the final layer and the first layer, like the embedding and the feed forward at the end. And that would still get you to amazing results that sometimes could beat models that have been designed for this problem. So to answer your question, and that's a great question, it's coming from the fact that the attention mechanism captures a sort of computational primitive and computational richness, for lack of a better word, that works very, very well. And that also means that you as a practitioner, you could start actually with a pre-trained model, just do what I just told you, and you might actually get very good results without having to spend, a few petaflops of compute budget. So it's an exciting time.
Thank you, Karim. That was the only question we have. So thank you, everyone, and every participant and every speaker today. And for all the participants, you can find in the chat the links for the GitHub repos. And thank you all. See you in our next event.
Thanks a lot. See you guys soon. Yeah.
Thank you.